Have you ever gazed up at the night sky and wondered if there's a deeper order to it all? A hidden design beneath the chaos of exploding stars, swirling galaxies, and the vast emptiness between them. For centuries, this question has captivated scientists, philosophers, and dreamers alike. They've searched for pattern symmetries so profound they might just hold the key to understanding the universe itself. And what they've uncovered is nothing short of breathtaking. Today, we're diving deep into one of the most compelling mysteries of modern cosmology, the universe's hidden symmetry. Far from being random or disordered, our cosmos appears to be built upon elegant, almost mathematical principles that repeat across scales from the tiniest particles to the largest structures in existence. These aren't just abstract ideas, they're clues left behind by the universe, waiting for us to piece them together. And as we'll discover, some of the most brilliant minds in history have proposed theories so revolutionary, they challenge everything we thought we knew about reality. In this video, we'll explore 30 of these astonishing theories, each one a window into the hidden architecture of existence. From symmetries that govern the behavior of light and matter to cosmic patterns that hint at multiple dimensions or even parallel universes, we're about to embark on a journey that will reshape how you see the cosmos. This isn't just science, it's a story of curiosity, imagination, and the relentless human drive to find meaning in the magnificent unknown. So settle in, open your mind, and get ready to see the universe in a whole new light. To begin our journey, let's look at one of the most elegant and mathematically beautiful ideas in modern physics, supersymmetry, often called SUSY. This theory suggests a stunning, hidden partnership at the very heart of reality, a kind of cosmic dance between the two fundamental families of particles that make up our universe. On one side, you have the fermions. These are the particles of matter, the building blocks of everything you can see and touch, the electrons orbiting an atom's nucleus, and the quarks that form protons and neutrons within that nucleus. They are the stubborn individualists of the particle world, refusing to occupy the same space. On the other side, you have the bosons. These are the force carriers, the messengers of nature's fundamental interactions. The photon carries the electromagnetic force, gluons carry the strong nuclear force that holds atomic nuclei together, and the W and Z bosons carry the weak nuclear force responsible for radioactive decay. Bosons are the sociable ones, perfectly happy to pile on top of one another. Supersymmetry proposes that for every known fermion, there should be a supersymmetric bosonic partner, and for every known boson, a supersymmetric fermionic partner. Imagine an unseen, shadow universe of particles, a perfect mirror image of the one we know. An electron, a fermion, would have a partner called a selectron, a boson. A photon, a boson, would have a partner called a photino, a fermion. This isn't just a whimsical idea, it solves some of the most nagging problems in physics. Take the hierarchy problem, the incredible weakness of gravity compared to the other forces. Our current math suggests the Higgs boson's mass should be driven to an astronomically high value by quantum fluctuations, yet it remains relatively light. SUSY elegantly cancels out these problematic calculations because the contributions from fermions and their new boson partners have opposite signs, balancing the equations and preserving the delicate structure of our universe. Perhaps even more compelling is SUSY's potential link to one of cosmology's greatest mysteries, dark matter, that invisible, mysterious substance that holds galaxies together with its gravity vastly outweighs all the ordinary matter we can see. What is it made of? Supersymmetry provides a perfect candidate. The lightest of these new supersymmetric particles, often thought to be the neutralino, would be stable, electrically neutral, and would only interact through gravity and the weak force, exactly the properties we predict for a dark matter particle. It's a proposal that connects the impossibly small world of quantum particles to the grand scale of galactic clusters. While experiments at the Large Hadron Collider have yet to find direct evidence for these superpartners, the mathematical elegance and explanatory power of supersymmetry keep it at the forefront of theoretical physics, a tantalizing hint of a more symmetric and ordered cosmos just beyond our current reach. But if supersymmetry hints at a shadow universe of particles, then our next theory completely reimagines the very fabric of spacetime itself. This is the realm of string theory, a framework so radical it proposes that the fundamental building blocks of the universe are not point-like particles but unimaginably tiny, vibrating strings. And within this elegant idea lies a profound hidden symmetry that could unite all of nature's forces. Think of it like this. In our everyday experience, a violin string can vibrate in different ways to produce distinct musical notes. A single G string can create a rich low note or a soaring high harmonic. String theory applies this same concept to the universe's most basic level. Each minuscule string, far smaller than any particle we've ever detected, vibrates at a specific frequency. One particular pattern of vibration might give rise to an electron, while a different, more energetic vibration creates a quark or a photon. In this stunning vision, every particle and every force is simply a different note on the cosmic symphony performed by these fundamental strings. This is a symmetry of a higher order, where the distinction between matter and force simply melts away. They are all manifestations of the same underlying entity. But to make the mathematics of this vibrating string symphony work, the theory demands something extraordinary. Our universe must have more than the three spatial dimensions we know. We are intimately familiar with moving forward and backward, left and right, and up and down. String theory, however, requires extra spatial dimensions, 6 or 7 of them, curled up into a shape so infinitesimally small that they are completely hidden from our perception. The geometry of these extra dimensions is described by intricate shapes known as Calabi-Yau manifolds. These are not simple shapes like spheres or cubes. They are complex, multi-dimensional forms with a specific, beautiful property. They preserve a quantum symmetry known as supersymmetry. The precise form of a Calabi-Yau manifold determines the vibrational patterns that are possible for the strings, which in turn dictates the laws of physics in our observable, four-dimensional world. The number of particle families, the strength of forces like electromagnetism, and the very existence of the electrons and quarks that build our reality could all be consequences of the hidden geometric symmetries within these folded-up dimensions. It's a breathtaking proposition. The reason gravity appears so weak compared to the other forces might be because it is partly leaking into or diluted across these additional spatial dimensions. The deepest symmetries of the cosmos may not be written in the particles we see, but in the secret geometric heart of reality itself, a place where the universe's most fundamental rules are composed as vibrations in a higher dimensional space. And yet, for all its elegance, string theory presents a truly mind-bending challenge to our perception of reality. If we accept that the true nature of the cosmos might involve these hidden, higher dimensions, it forces us to ask an even more profound question. Are the three dimensions we experience every day even real? This leads us to one of the most radical and startling ideas in all of physics, the holographic principle. This theory dares to suggest that our entire three-dimensional universe, with all its galaxies, stars, planets, and us, might not be the fundamental reality. Instead, it could be a magnificent and incredibly detailed projection, a hologram generated from a two-dimensional surface at the very edge of the cosmos. The seeds of this incredible idea were first planted not by looking out at the vastness of space, but by staring into the abyss of a black hole. A black hole is defined by its event horizon, the point of no return beyond which not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's event horizon has a property we usually associate with disordered systems: entropy. Entropy is a measure of the number of ways you can rearrange the microscopic components of a system without changing its overall appearance. It's a measure of hidden information. Wittgenstein found that the entropy of a black hole, essentially the amount of information it contains, is not proportional to its volume as you might expect for a three-dimensional object. It is proportional to the surface area of its event horizon. This was a huge clue. It suggested that all the information needed to describe everything that has ever fallen into a three-dimensional black hole is somehow encoded on its two-dimensional boundary. This finding was so revolutionary that it led to a new law of physics, the holographic principle. It proposes that the maximum amount of information that can possibly exist within any region of space is not determined by its volume, but by the area of the surface that encloses it. To understand this, think of a more familiar hologram like the kind you might see on a credit card. That shimmering, three-dimensional image isn't truly 3D. It is projected from a flat, two-dimensional film etched with microscopic patterns. The holographic principle applies this same logic to the entire universe. The galaxies, nebulae, and everything within the cosmos that we perceive in three dimensions could be a projection of information stored on a distant, two-dimensional surface that surrounds us. In this view, our reality is a cosmic illusion, a translation of data from a simpler, lower-dimensional reality into the rich, multi-dimensional experience we inhabit. The implications of this are staggering. It suggests a profound and hidden symmetry between dimensions, a fundamental equivalence between a volume of space and its boundary. The laws of physics that govern our 3D world could be emergent properties arising from complex interactions playing out on a distant 2D screen. This principle could be the key to resolving one of the biggest paradoxes in physics, the black hole information paradox. If you throw an encyclopedia into a black hole, does the information within it truly vanish forever, violating quantum mechanics? The holographic principle says no. That information isn't lost, it is meticulously preserved, imprinted on the event horizon itself, like data encoded on the surface of a DVD. Our perception of a rich, three-dimensional reality may be the universe's most sophisticated and convincing illusion, a grand cosmic show whose source code is written in two dimensions. If the holographic principle suggests our reality might be a projection from a lower dimensional surface, it forces us to reconsider the very nature of space and the rules of geometry that govern it. This brings us to a different, yet equally profound type of symmetry, one that isn't about mirror images or extra dimensions, but about scale itself. This is conformal symmetry, a principle where the angles between lines are preserved even as distances are stretched or shrunk. Imagine taking a detailed map of a city. If you were to zoom in on a single neighborhood or zoom out to see the entire continent, the shapes of the streets and the angles at which they intersect would remain exactly the same. The map might change in size, but its internal geometry, its essence, stays consistent. That preservation of local angles, regardless of scale, is the heart of conformal symmetry. It's the idea that the laws of physics might not care about absolute size, only about relative proportions. This concept isn't just a mathematical curiosity. Many physicists believe it could have been the reigning symmetry of the very early universe. In the first fleeting moments after the Big Bang, the cosmos was an incredibly hot, dense, and energetic soup. Under such extreme conditions, the concept of a fixed, absolute distance may have had no meaning. Particles and energy would have been so energetic that their behavior could have been scale invariant, a process that looks the same whether you examine it on a microscopic scale or a cosmic one. In this conformally symmetric phase, the universe wouldn't have had a preferred ruler. The fundamental forces, perhaps even including gravity, might have been unified under this elegant principle. It offers a potential window into a simpler, more symmetric origin before the universe cooled and expanded, breaking this perfect symmetry and giving rise to the distinct forces and particles we see today. We can even observe echoes of this symmetry in certain phenomena today. Consider the intricate patterns of a snowflake or the branching structure of a lightning bolt. These are fractals, shapes that exhibit self-similarity. They look roughly the same at different levels of magnification. This is a type of scale invariance, a cousin to conformal symmetry. In the realm of quantum field theory, some of the most powerful and successful theories we have, like quantum electrodynamics, exhibit conformal symmetry at certain energy levels. This symmetry places incredibly tight constraints on how particles can interact, simplifying the complex mathematics and allowing physicists to make precise, testable predictions. The implications of conformal symmetry for understanding the universe's fundamental structure are staggering. If true, it suggests that the vast cosmos we inhabit, with its galaxies and nebulae, and the quantum world of buzzing particles, might both be governed by the same underlying geometric principle, a principle that transcends size. It hints at a deep and hidden order where the universe's blueprint is written not in fixed distances, but in angles and relationships, a cosmic design that remains invariant from the smallest scales to the largest. This profound symmetry we see in the geometry of the universe finds a remarkable parallel in the fundamental laws that govern particles and their interactions. If we want to talk about a symmetry that is woven into the very mathematical fabric of our most successful physical theories, we must turn our attention to CPT symmetry. This is not a symmetry of shape or scale, but a symmetry of transformation, and it is considered to be one of the most sacred principles in all of physics. The acronym stands for the combined operations of charge conjugation, parity, and time reversal. To understand its power, we need to break down what each of these actions means on its own. Charge conjugation, or C, is the act of swapping every particle in a system with its corresponding antiparticle. Imagine an electron peacefully orbiting an atomic nucleus. Apply the C operation, and that electron is instantly replaced by a positron, its antimatter twin, which has the same mass but a positive electric charge instead of a negative one. Next is parity, or P. This is a kind of mirror transformation. It takes the entire system and creates its perfect mirror image, flipping the spatial coordinates. What was on the left is now on the right. What was moving up is now moving down. It's like watching the universe in a mirror. Finally, there is time reversal, symbolized by T. This is exactly what it sounds like. It reverses the arrow of time. A movie of particles moving and interacting is played in reverse. A ball rolling away from you would, under T, roll back toward you. For a long time, physicists believed that each of these symmetries was individually perfect and unbreakable, that the laws of physics would work exactly the same in a world made of antimatter, or in a mirror universe, or if time ran backwards. But then came a series of shocking discoveries. In the 1950s, physicists Tsung Dao Li and Chen Ning Yong proposed that the weak nuclear force, the force responsible for radioactive decay, might actually violate parity symmetry. This was quickly confirmed in a famous experiment led by Qin Xiong Wu, which showed that certain radioactive decays were not mirror symmetric. The universe, at a fundamental level, has an inherent handedness, a preference for left over right. Later, it was found that the combined operation of C and P could also be violated. This was another major blow to our idea of a perfectly symmetric cosmos. But then, a miracle of theoretical physics emerged. Even though C, P, and even CP can be violated individually, the combined operation of all three together, swapping particles for antiparticles, reflecting the universe in a mirror, and reversing the flow of time, appears to be absolutely perfect. As far as every experiment has ever been able to show, the laws of physics are completely invariant under a CPT transformation. This is a cornerstone of quantum field theory. It means that if you could create an antimatter universe that is the mirror image of our own and where time flows backwards, it would be utterly indistinguishable from our own universe. The processes that govern it would follow exactly the same rules. This deeply profound connection suggests that matter and antimatter, left and right, forward and backward in time, are not independent concepts but are fundamentally linked in a tripartite symmetry. This near-perfect symmetry makes its one potential imperfection all the more significant and mysterious. We know our observable universe is made almost entirely of matter, with very little antimatter to be found. This is the great matter-antimatter asymmetry problem. If the Big Bang created equal amounts of matter and antimatter, as CPT symmetry would seem to demand, they should have annihilated each other, leaving behind a universe filled with nothing but light. The fact that we exist at all is proof that some process in the early universe favored matter, creating a tiny, 1 in a billion excess that built everything we see. The sacredness of CPT symmetry means this imbalance cannot come from a violation of CPT itself. Instead, cosmologists believe the answer lies in a violation of CP symmetry in the early universe. Processes involving certain exotic particles must have behaved slightly differently than their antimatter mirror images, a subtle bias that, over time, filtered out most of the antimatter. The unwavering perfection of CPT symmetry acts as a guiding light, telling us that the secret to our existence must lie not in a flaw in this ultimate symmetry, but in the breaking of a lesser one, a cosmic preference etched into the laws of physics during the universe's first moments. Now, if the idea of these hidden Calabi-Yau dimensions shaping our reality is mind-bending, prepare for a concept that takes this geometric elegance to an entirely new level of profundity: mirror symmetry. This is a discovery so unexpected and powerful that it fundamentally altered how physicists and mathematicians view the relationship between the shape of the universe and the laws that govern it. At its heart, mirror symmetry proposes an astonishing possibility: two Calabi-Yau manifolds that look completely different to a mathematician, with different shapes, different holes, and different numbers of dimensions curled up in specific ways, can, in fact, describe the exact same physical universe. Imagine you have two violins. One is a classic Stradivarius, crafted from aged maple and spruce with a specific curvature to its body. The other is a radically modern design, made from carbon fiber with a completely alien geometric shape. To your eye, they are utterly different instruments, but when you play them, they produce not just similar notes, but identical music. Every chord, every harmonic, every subtle resonance is exactly the same. This is the essence of mirror symmetry in string theory. The two violins are like two mirror Calabi-Yau shapes. They appear mathematically distinct, but from the perspective of the strings vibrating within them, they are physically equivalent. The physics they produce, the particle masses, the force strengths, the very laws of nature in the observable four-dimensional world are indistinguishable. This revelation emerged from studying a specific type of string theory and the way strings wrap around the holes and loops within these complex shapes. Physicists found that for a given Calabi-Yau manifold with a certain number of holes of one type, there could always be a mirror partner with a completely different arrangement of holes. The calculations for a complex physical process in one geometry, which might be incredibly difficult to solve, could become dramatically simpler when translated into the language of its mirror partner. It was like finding a secret back door into solving the universe's most complicated equations. A problem that looked intractable in one geometric picture would suddenly become elegant and clear in the other. The implications of this are staggering. It suggests that the physical reality we experience is not uniquely tied to a single, specific geometry of the hidden dimensions. There isn't one true shape to the universe's extra dimensions. There could be multiple, equally valid geometric descriptions that all lead to the same physics we see. This introduces a profound form of redundancy into the very fabric of existence, a hidden symmetry that says our description of reality is not absolute. The universe, in its deepest layers, might be far more flexible and interconnected than we ever imagined, with vastly different mathematical starting points converging on the single, consistent physical world we call home. It's a powerful reminder that the true nature of reality may lie not in the geometry itself, but in the invariant physical laws that emerge from it. This profound connection between seemingly different geometric descriptions in mirror symmetry finds an even more radical expression in a theory that is arguably one of the most significant breakthroughs in theoretical physics of the last few decades, the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. This is not merely a symmetry, it's a full-blown duality, a complete equivalence between two descriptions of reality that, on the surface, could not appear more different. It's the ultimate hidden symmetry, suggesting that a theory of gravity warping the fabric of spacetime in a higher dimensional universe is exactly the same thing as a theory of particles and fields dancing on that universe's lower dimensional boundary with no gravity at all. To grasp this astonishing idea, we need to understand the two sides of this cosmic coin. First, imagine a special kind of universe called anti-de Sitter space, or AD-S. This isn't our universe. Our cosmos is expanding at an accelerating rate, which cosmologists describe as de Sitter space. AD-S is its hypothetical, gravity-rich cousin. Picture it as a cosmic chamber with a very distinct feature. Its center pulls strongly, while its outer boundary acts like a perfect, reflective wall. If you shine a light beam from the center toward the boundary, it would travel outward, reflect off the wall, and return to the center in a finite amount of time. It's a self-contained universe with a clear, defined edge. On one side of the AD-S/CFT duality, we have a theory of quantum gravity playing out in the bulk of this AD-S universe. This involves all the mind-bending concepts we've been exploring: strings vibrating, black holes forming and evaporating, the very fabric of space-time bending and curving under the weight of mass and energy. It's a complex, multi-dimensional world. Now, here is the breathtaking part of the proposal. The AD-S/CFT correspondence states that this entire, complicated theory of gravity in the bulk is completely and exactly equivalent to a conformal field theory, a specific type of quantum theory that lives only on the boundary of that AD-S space. This boundary has one less dimension, so a gravitational drama in 5-dimensional AD-S space is perfectly mirrored by a particle physics play on its 4-dimensional boundary. This means that every single event, every interaction, every wobble of a string in the gravitational interior has a perfect counterpart in the interactions of particles and fields on the non-gravitational boundary. A black hole warping spacetime in the center of the AD-S universe is described by a specific, hot, dense state of the quantum field theory on the boundary. The process of something falling into that black hole is translated into a very specific and complex scrambling of information within that boundary theory. They are two languages describing the very same reality. This is the holographic principle we discussed earlier, but made mathematically precise and powerful within this specific context. It's as if the entire 3-dimensional movie of our reality, complete with all its special effects of gravity, is being projected from a 2-dimensional source code written in the language of particles. The implications of this for solving physics' greatest puzzles are immense. The black hole information paradox, for instance, becomes far less paradoxical. In the boundary theory, which is a well-understood quantum system, information can never be lost. It just gets chaotically scrambled. Because the two descriptions are equivalent, that information must also be preserved in the gravitational description, even as it falls into a black hole. It provides a concrete mathematical framework where the holographic principle isn't just a suggestive idea, it's a calculable tool. Perhaps most philosophically striking, AD-S/CFT suggests that spacetime itself and the force of gravity may not be fundamental. They could be emergent phenomena, collective illusions that arise from the complex quantum entanglement of vast numbers of simpler, non-gravitational degrees of freedom living on a lower dimensional surface. We are not living in a simulation. In a very real mathematical sense, we are the simulation, a breathtakingly real and physical projection from a simpler, more fundamental layer of reality. This hidden symmetry between the inner volume and the outer boundary is one of the strongest clues we have that our intuitive understanding of the universe is merely the surface of a far deeper and far more strange truth. Now, as we move from the cosmic hologram and the symmetries of dimensions, we encounter a profound duality that strikes at the very heart of the forces that shape our reality. This is electric-magnetic duality, a stunning symmetry that reveals a deep and hidden partnership between two phenomena we often think of as separate: electricity and magnetism. We all learn the basics in school, that moving electric charges create magnetic fields, and changing magnetic fields can induce electric currents. This relationship is the foundation of everything from electric generators to the device you're using to watch this video. But this classic connection is just the surface of a far more mysterious and elegant symmetry that operates at the deepest quantum level. The story of this deeper duality begins with one of the most brilliant and visionary physicists of the 20th century, Paul Dirac. In the early 1930s, Dirac was wrestling with the equations of quantum mechanics, attempting to describe the electron in a way that was consistent with both quantum theory and Einstein's theory of special relativity. In the process, he made a startling prediction. His equations didn't just describe the electron, they also implied that magnetism might have a fundamental, indivisible unit, just as electricity has the electron. He theorized the existence of a magnetic monopole, a particle that would be just a pure north pole or a pure south pole, not attached to its opposite. Think of a magnet from your fridge. It always has two poles. If you break it in half, you don't get a separate north and a south. You get two smaller magnets, each with its own pair of poles. A magnetic monopole would be different. It would be the magnetic equivalent of an electron, a single, isolated pole. Dirac's work showed something even more incredible. The mere existence of just one such magnetic monopole anywhere in the universe would provide a stunning explanation for one of physics' greatest puzzles: why electric charge comes in discrete, quantized packages. Why is the charge of an electron exactly equal and opposite to that of a proton? Why is it that specific fixed value and not some other? Dirac found that if a magnetic monopole exists, then electric charge must be quantized. The product of the electric charge and the magnetic charge would be an integer multiple of a fundamental constant. This is a profound connection, a hidden symmetry where the very existence of a magnetic particle would dictate the rules for all electric particles. It suggests that the quantization we see everywhere in the quantum world might not be a random feature, but a necessary consequence of a deeper, dualistic structure woven into the fabric of the cosmos. While a lone magnetic monopole has yet to be discovered in experiments, the idea of electric-magnetic duality has flourished and evolved into one of the most powerful concepts in modern theoretical physics. This duality is not just about swapping electrons for hypothetical monopoles. It proposes that in certain quantum field theories, our description of the world can be completely transformed. What we perceive as a theory of strongly interacting particles, where forces are incredibly intense and calculations are nearly impossible, can be exactly equivalent to a theory of weakly interacting particles, where the math becomes simple and elegant. It's like having a map of a complex, mountainous terrain that is incredibly difficult to navigate, and then discovering a second map of the same region that shows it as a perfectly flat, easy-to-cross plain. Both maps describe the exact same reality, but one perspective makes the journey effortless. This powerful form of duality appears in several advanced frameworks, most notably in supersymmetric theories. Here, it's often called S-duality. In this context, a theory with a large electric charge and a weak coupling constant, meaning particles interact infrequently and gently, can be completely equivalent to its dual theory, which has a large magnetic charge and a strong coupling constant, where interactions are fierce and constant. This is a symmetry that allows physicists to solve problems that were previously thought to be intractable. They can take a question about the behavior of particles in a regime where our mathematical tools are useless, translate it using this duality into a question about a different set of particles in a regime where the math is manageable, solve it easily, and then translate the answer back. It's a master key that unlocks doors to understanding the strong nuclear force that binds quarks together inside protons and neutrons. This incredible symmetry hints that what we call elementary might depend on our perspective. In one description, an electron is a fundamental, point-like particle, but in the dual magnetic description, that same electron might be seen as a composite object made up of more fundamental magnetic monopoles. This challenges our very notion of what is truly fundamental in the universe, suggesting a beautiful and deep democracy in nature where electricity and magnetism are not just partners, but are two sides of the very same coin, offering us different windows into a single, unified reality. This journey into the deepest symmetries of the cosmos has revealed a universe far more interconnected and flexible than we ever imagined. But what about symmetry that isn't about swapping particles or dimensions, but about the very scale of reality itself? This brings us to a principle that is both beautifully simple and profoundly powerful: scale symmetry, or conformal invariance. This is the idea that the fundamental laws of physics might not care about absolute size. A process governed by this symmetry would look exactly the same whether you were observing it through a microscope with your own eyes or through a telescope aimed at a distant galaxy. The angles and relationships between objects remain constant, even as distances stretch or shrink. We can actually observe echoes of this symmetry in our everyday world. Consider the intricate branching pattern of a frost crystal forming on a window pane. Look closely and you'll see that the larger branches themselves are made of smaller, nearly identical branches. This self-similarity across different scales is a hallmark of fractal geometry and is a direct manifestation of approximate scale invariance. The universe seems to love these patterns. They appear in the sprawling structure of a river delta, the furious path of a lightning bolt, and even in the way galaxies cluster together in vast cosmic webs. These are all systems operating at a critical point, a state of delicate balance where scale symmetry emerges in all its glory. The true power of this concept is unlocked through a brilliant theoretical framework known as the renormalization group. Think of this not as a single group, but as a process, a way of understanding how a physical system changes as you zoom in or out. Imagine you're using a camera with a digital zoom. As you zoom in on a photograph, individual pixels become visible, and the image might appear blocky and coarse. Zoom out, and those fine details blend together to create a smooth, continuous picture. The renormalization group is the mathematical tool that allows physicists to understand how the pixels of our universe, its fundamental parameters like the strength of forces and the masses of particles, change as we change the energy scale or resolution at which we're looking. This process reveals that most physical systems are not scale symmetric. The strength of the electromagnetic force, for instance, actually depends on the distance between charges. It's stronger at close range and weaker farther away, a phenomenon known as screening. This is a clear breaking of scale symmetry. However, at special points known as fixed points, this zooming process reveals something extraordinary. Here, the parameters stop changing. No matter how much you zoom in or out, the system looks precisely the same. It becomes truly scale invariant. These critical points are where phase transitions occur, like the moment water is poised perfectly between its liquid and gaseous states, or the exact instant a magnet loses its magnetization as it's heated. At these fleeting moments of transformation, the system is buzzing with fluctuations on every conceivable scale, from the microscopic to the macroscopic, and scale symmetry reigns supreme. This has a breathtaking implication for the origin of our universe. Many cosmologists believe that the very early cosmos, in the first instance after the Big Bang, was in such a critical high-energy state. In that seething, ultra-hot primordial fireball, the concept of a fixed, absolute distance may have had no meaning. The universe could have been perfectly scale-symmetric, a fractal-like state where the laws of physics were invariant no matter how you stretched or shrunk your perspective. In this vision, the fundamental forces, electromagnetism, the strong and weak nuclear forces, and even gravity, were not distinct but unified under this elegant, overarching principle. So, if the early universe was in this perfectly symmetric state, how did we end up with the world we see today, filled with objects of definite size and particles with specific mass? The answer lies in the breaking of scale symmetry. As the universe expanded and cooled, it fell out of its critical state. This is analogous to what happens when you slowly cool a magnet. At a high temperature, it is disordered and symmetric. There is no preferred direction. But as it cools past its critical temperature, it suddenly chooses a direction to magnetize, spontaneously breaking the symmetry and giving rise to a specific magnetic field. In the cosmos, this cooling process triggered a cosmic phase transition. The perfect scale symmetry was broken, and in that breaking, the masses of particles like the electron and quark were generated. What was once a massless, scale-inverse world gained structure, hierarchy, and form. The Higgs mechanism, which gives mass to fundamental particles, can be seen as the direct result of this symmetry breaking. The mass of everything from the tiniest particle to the largest star is not a primary feature of the universe, but a relic, a frozen-in artifact of the moment the cosmos lost its perfect scale invariance and chose a specific, concrete reality. But this grand cosmic narrative of symmetry breaking and the emergence of mass leads us to a profound and very specific question about the building blocks of our existence. We are made of atoms, and those atoms are built from two distinct families of particles. In one family, we have the baryons, the protons and neutrons that form the nucleus of every atom. In the other, we have the leptons, the electrons that orbit that nucleus. For a long time, these were seen as two separate and independent dynasties, each playing by their own rules. But what if, at the most fundamental level, they are not separate at all? This brings us to a compelling and deeply hidden symmetry, the symmetry between baryons and leptons. To understand why this idea is so powerful, we need to look at two of the universe's most carefully guarded quantities, baryon number and lepton number. In the standard model of particle physics, these are considered conserved quantities. Think of them like cosmic accounting rules. In any particle reaction, the total baryon number must stay the same. A proton, which has a baryon number of 1, cannot just vanish or decay into lighter particles on its own because that would reduce the total baryon number to 0, breaking the conservation law. Similarly, the total lepton number is conserved. An electron has a lepton number of 1, and it too must be accounted for in every interaction. These laws are why the protons in our bodies are stable. They are essentially immortal, and that stability is the foundation for the existence of all complex matter. Yet, there is a glaring cosmic paradox that these conservation laws cannot explain on their own. As we touched on earlier, the Big Bang should have created equal amounts of matter and antimatter. A baryon number of 0, but we live in a universe overwhelmingly dominated by matter. Somehow, an initial symmetry was broken, producing a tiny excess of baryons over antibaryons, roughly 1 extra quark for every billion quark-antiquark pairs. This is the baryon asymmetry problem. The key to solving it, many physicists believe, is that baryon number is not perfectly conserved. It must be capable of being violated, but only under very special conditions. This is where the symmetry with leptons comes into play. Grand unified theories, or GUT, are ambitious frameworks that seek to merge the electromagnetic, weak, and strong nuclear forces into a single, unified force that would have existed in the extreme energy of the early universe. And one of the most dramatic predictions of these theories is that they inherently treat quarks, the constituents of baryons and leptons, as different manifestations of the same fundamental entity. In a grand unified theory, a quark can transform into a lepton. This directly violates the separate conservation of baryon and lepton number. However, these theories often conserve the difference between baryon number and lepton number, a quantity known as B-L. This reveals a profound hidden link asymmetry between these two seemingly separate families. They are not independent, they are two sides of a single coin, and processes can change one as long as they correspondingly change the other. The most famous experimental signature of this deep connection is the predicted decay of the proton. If baryon number is not sacred, then the proton, the bedrock of stable matter, should not be immortal. Grand unified theories predict that a proton can decay, for instance, into a positron and a pion. In doing so, its baryon number decreases by 1, but it creates a lepton, the positron, with a lepton number of 1. The total BL can remain balanced. This isn't just a minor prediction. It's a fundamental test of the entire unified concept. For decades, enormous experiments like Supersymmetry and in Japan have been watching thousands of tons of ultra-pure water for the telltale flash of light that would signal the death of a single proton. While we haven't seen it yet, the search continues because the discovery of proton decay would be one of the most monumental breakthroughs in physics, providing direct evidence for this grand unification and the hidden baryon-lepton symmetry. This symmetry doesn't just explain how protons could decay, it also provides one of the most elegant mechanisms for generating the matter-antimatter asymmetry in the first place, a process known as leptogenesis. The idea starts with the decay of incredibly heavy, hypothetical particles that exist only at those grand unification energy scales. These decays could preferentially produce more leptons than antileptons, violating lepton number. But thanks to a known and observed phenomenon in the weak nuclear force called Sphaleron processes, this lepton asymmetry can be converted into a baryon asymmetry. These sphalerons are capable of violating both baryon and lepton number while conserving BL. So, an initial excess of leptons created in the fiery first moments of the universe can be transformed by these processes into the excess of baryons that we are made of today. In this breathtaking scenario, the very stuff of our being, the protons and neutrons in every atom of our bodies, may have originated from a primordial asymmetry in the lepton family, all made possible by the profound and hidden symmetry that binds their fates together. This concept of profound symmetries linking different families of particles finds a more subtle yet equally powerful expression in the strong nuclear force itself. To understand the glue that holds atomic nuclei together, we must venture into the complex world of quantum chromodynamics, or QCD, the theory that describes how quarks interact via gluons. At extremely high energies, like those in particle colliders, this force is relatively weak, and quarks behave almost like free particles, a property known as asymptotic freedom. But in the quiet, low-energy world of our everyday reality, the strong force becomes incredibly intense. This is the regime where quarks are forever confined within protons and neutrons, and where the mathematics of QCD becomes notoriously difficult to solve directly. It is here, in this challenging low-energy landscape, that a beautiful and highly effective theoretical tool emerges: hidden local symmetry. This approach doesn't replace QCD. Instead, it provides a powerful and intuitive way to approximate its behavior, revealing a stunning hidden structure within the chaos. The story begins with the pions. These are the lightest members of the meson family, particles made of a quark and an antiquark. In the limit where the up and down quarks are considered massless, a simplification that works surprisingly well. the theory of the strong force possesses a fundamental global symmetry. This means the equations are invariant under a certain kind of rotation in the abstract space of quark flavors. Due to a quantum effect, this symmetry is not manifest in the vacuum state of the universe. It is spontaneously broken. A powerful theorem, Goldstone's theorem, tells us that whenever a continuous symmetry is spontaneously broken in this way, new massless particles must appear. These are called Nambu-Goldstone bosons, and in QCD, the pions are these particles. They are the gentle ripples in the field that arise from the broken symmetry. Because they are massless in this idealized limit, they are very easy to excite and dominate the low-energy dynamics of the strong force. This is the foundation of chiral perturbation theory, a framework for making predictions about low-energy, strong interactions by systematically expanding in the energies and masses of the pions. Now, where does the hidden part come in? The key insight was that the theory describing these massless pions itself has a further hidden symmetry. This symmetry is local, meaning it can vary from point to point in spacetime, unlike a global symmetry which is the same everywhere. To make the theory consistent with this newly discovered local symmetry, physicists must introduce new fields. These fields are the gauge fields, and they correspond to new particles, in this case the rho meson and its partners. The rho meson is a heavier, short-lived particle that acts as the force carrier for the strong interactions between pions themselves. So, what began as a theory of free, massless pions is transformed, by revealing this hidden local symmetry, into a theory that includes the massive force-carrying rho mesons that govern their interactions. This is a profoundly elegant revelation. The rho meson isn't just randomly inserted. It emerges naturally as the necessary gauge boson required to restore a local symmetry that was secretly present all along in the pion dynamics. This approach provides a remarkably successful effective description of the strong force at low energies. It allows physicists to calculate the scattering of pions off each other, the decay rates of heavier mesons, and the properties of atomic nuclei with a clarity that was previously impossible using the raw, complex equations of QCD directly. By uncovering this hidden local symmetry, we gain a powerful lens through which to view the messy, low-energy world of nuclear physics, transforming it from an intractable problem into a landscape of elegant, predictable order. But if the symmetries of the strong force can be revealed through clever theoretical frameworks, what does that tell us about the most fundamental stage of all, the stage of spacetime itself? We've journeyed through symmetries of particles, forces, and dimensions, but we must now confront perhaps the most radical idea of all, that the arena where all this physics plays out might not be fundamental. This is the mind-bending proposition of emergent spacetime symmetry, a cutting-edge concept suggesting that the geometry of the universe and the very laws of motion we take for granted are not primary features of reality, but rather a collective illusion that arises from something far more basic. We all experience the smooth, continuous fabric of spacetime. We move through 3 dimensions of space and 1 of time, governed by the relentless speed limit of light, a principle known as Lorentz invariance. This symmetry is the bedrock of Einstein's theory of special relativity. It ensures that the laws of physics are the same for all observers moving at constant velocity relative to each other. For over a century, this has been treated as an inviolable, fundamental truth of nature. But what if it isn't? What if Lorentz invariance is not a rule written into the foundation of the cosmos, but a behavior that emerges on large scales, much like the smooth flow of water emerges from the chaotic jostling of countless individual molecules? This idea gains traction from our ongoing struggle to reconcile gravity with quantum mechanics. In our current theories, spacetime is a classical, smooth background. But when we try to quantize it, to describe it in the same probabilistic terms as particles and forces, the mathematics breaks down, producing infinities. This suggests that at the tiniest possible scales at the Planck length, the smooth, continuous nature of spacetime must give way to something else, a discrete, grainy, and fundamentally quantum substructure. Think of a digital photograph on your screen. When you zoom in far enough, the smooth image dissolves into individual pixels. Emergent spacetime posits that reality itself has a kind of pixelation, and what we perceive as a smooth, symmetric continuum is actually a large-scale approximation. So, if spacetime is not fundamental, what is it made of? The leading candidate is quantum information specifically, the quantum entanglement between the basic building blocks of this substratum. In this view, the distance between 2 points in space is not a primary property. Instead, it is a measure of how entangled they are. Two highly entangled quantum systems are effectively close to one another, while systems with little to no entanglement are far apart. The geometry of space itself could be woven from this web of quantum connections. This provides a stunning explanation for the DEEPEST Chinese letter of gravity described by Einstein's general relativity. The famous equation E equals mc squared tells us that energy and mass are equivalent, and since all energy has a quantum information content, the distribution of mass and energy in a region, which tells spacetime how to curve, might actually be a representation of the underlying entanglement structure. A massive object like a star would then distort spacetime because it dramatically alters the quantum information content of its surrounding volume. This leads to an even more profound implication for symmetry. The Lorentz invariance we observe, the fact that the speed of light is constant for all observers, may not be a fundamental law of the deeper theory. It could be an emergent property, an accidental symmetry that arises because the microscopic quantum system from which spacetime emerges happens to be arranged in a specific, critical way that looks smooth and symmetric from our low-energy, large-scale perspective. It would be an effective symmetry, incredibly accurate and robust for all the physics we can currently probe, but one that could potentially break down at energies approaching the Planck scale. Some quantum gravity models, like loop quantum gravity or certain formulations of string theory, predict tiny, observable violations of Lorentz invariance at these extreme energies. Experiments tirelessly search for these minuscule signatures, such as light of different energies traveling at very slightly different speeds across the universe, which would be the smoking gun that our smooth, symmetric spacetime is indeed a magnificent emergent phenomenon. But this elegant framework of gauging hidden symmetries and the radical idea of emergent spacetime have pushed our understanding to the very edge. Now, we must venture into a concept that fundamentally reshapes what we even mean by symmetry itself. This is the world of non-invertible symmetries, an idea so advanced it challenges the very definition that has guided physics for centuries. For generations, a symmetry operation was something you could always reverse. Rotate a square by 90 degrees and you can rotate it back. Reflect an image in a mirror and reflecting it again returns you to the start. Each transformation had a clear, unambiguous inverse. In the cutting-edge landscape of modern quantum field theory, physicists have discovered that this is not the whole story. They have uncovered a vast new class of generalized symmetries where this simple rule breaks down. These are non-invertible symmetry operations. Performing one of these operations is like passing through a mysterious, one-way door in the mathematical structure of a theory. You can pass through it to get to a new state, but you cannot simply reverse the step to return to where you started. The path back is either impossible, or it requires a completely different, more complex procedure. The operation essentially forgets some information about the original state, making a perfect reversal a mathematical impossibility. This isn't a flaw, it's a feature of a deeper, more exotic structure. To grasp this, imagine a special kind of transformation that acts on a quantum field. A standard symmetry might create a single distinct defect or a new field configuration. A non-invertible symmetry operation, however, might create a whole superposition of different states at once. It doesn't map one unique state to another unique state. Instead, it maps one state to a tangled quantum ensemble of possibilities. There is no simple, single operation you can perform to perfectly undo this and isolate the original state from the quantum fog it produced. The inverse, in the traditional sense, simply does not exist. These operations are described by more complex mathematical objects called category theory, which can describe these one-way relationships with perfect clarity. Why would such a bizarre-sounding concept be revolutionary? Because these non-invertible symmetries impose incredibly powerful new constraints on how a quantum field theory can behave. Just like their invertible cousins, they must be preserved by all physical processes. This means they place strict limitations on the kinds of particles that can exist, the ways they can interact, and even the possible outcomes of their collisions. They act as a stringent filter, ruling out countless hypothetical theories that might otherwise seem mathematically consistent, guiding physicists toward the ones that could truly describe nature. Their discovery has opened up a vast new classification system for quantum field theories, a periodic table of possibilities that is far richer and more intricate than anyone previously imagined. Perhaps their most profound application lies in the eternal quest for a theory of quantum gravity. String theory and other approaches predict a staggering number of possible stable universes, each with their own laws of physics, a dilemma known as the landscape problem. Non-invertible symmetries may provide the key to navigating this vast landscape. They could act as a selection principle, identifying which of these potential universes are actually physically consistent when all quantum effects are accounted for. A theory that possesses certain non-invertible symmetries might be robust against the quantum anomalies that destroy other theories, making it a viable candidate for our reality. In this view, the hidden symmetry that truly defines our universe and allows for the emergence of space-time and gravity might not be a simple, reversible rotation, but one of these deeper, more complex, and fundamentally one-way transformations operating at the very foundation of everything. Yet as we push the boundaries of symmetry into these exotic, non-invertible realms, we are also compelled to ask what happens when we extend symmetry in a more traditional, but equally profound direction into the domain of higher spin. All the fundamental particles we know and love possess a property called spin, an intrinsic form of angular momentum that comes in discrete units. The familiar photon, carrier of light, has a spin of 1. The graviton, the hypothetical particle believed to mediate gravity, is predicted to have a spin of 2. But what about particles with spin 3 or 4 or even higher? This is the fascinating world of higher spin symmetry, a theoretical playground where the rules of the game become both more constraining and potentially more revealing of nature's deepest secrets. The concept of a higher spin particle might seem like a simple incremental step, but it introduces dramatic consequences. The mathematics governing these entities is incredibly restrictive. For a massless particle, one that travels at the speed of light like the photon or graviton, having a spin greater than 2 imposes such stringent conditions on its interactions that it was long thought to be impossible for them to couple consistently with other fields in a flat Minkowski spacetime. These particles would be, in a sense, too symmetric for their own good, forcing interactions to behave in ways that seem to violate fundamental principles like causality or unitarity. For decades, this was a major roadblock, suggesting that our universe's particle content might be forever limited to spins 0, 1/2, 1, and 2. The breakthrough came from a dedicated and deep line of research now crystallized in Vassiliev theory, a sophisticated framework for describing interacting higher spin fields. Developed by physicist Mikhail Vassiliev and others, this theory doesn't just add a few high-spin particles to the existing mix. Instead, it proposes an infinite dimensional symmetry, a symmetry so vast it encompasses an entire tower of massless fields with every possible integer spin. In this picture, the photon and the graviton are merely the first two members of an infinite family of force carriers. The theory is formulated not in standard flat space, but in a space-time with a constant negative curvature, an anti-de Sitter space, the very same type of universe that plays a starring role in the AD/CFT holographic correspondence. This geometric context is crucial. It provides the necessary flexibility for these finicky higher spin particles to interact consistently without breaking the laws of physics. What makes Vasilev theory so compelling is its deep and natural connection to holography. The infinite-dimensional higher spin symmetry in the bulk of this AD space is holographically dual to a very specific kind of theory on the boundary. That boundary theory is often a vector model, a quantum field theory whose fundamental ingredients are a large number of simple field components, like arrows pointing in different directions, and whose global symmetry is remarkably large. The magic of the duality is that the higher spin symmetry in the gravitational bulk is mirrored by the conservation of an infinite number of higher spin currents on the boundary. Every time you add a new, higher spin field to the bulk gravity theory, it corresponds to a new conserved quantity, a new protected law, in the particle physics theory on the boundary. This provides one of the clearest and most mathematically precise examples of the holographic principle in action. A beautiful toy model where the entire dictionary between the gravitational world and the quantum world can be explored in explicit detail. This makes higher spin theories far more than a mathematical curiosity. They serve as a vital theoretical laboratory. They are a simpler, more symmetric cousin of a full-fledged theory of quantum gravity like string theory. By studying how this infinite tower of higher spin fields interacts and how its symmetry is realized, physicists can gain profound insights into the fundamental principles that must govern any consistent unification of gravity with quantum mechanics. They act as a guiding light, revealing how immense symmetry can dictate the structure of interactions and how those interactions might be projected across dimensions through the holographic lens. While we have not yet discovered these exotic higher spin particles in nature, their study continues to illuminate the path toward a deeper, more symmetric, and potentially complete description of the cosmos. Now, let's shift our perspective from the geometry of spacetime and the spin of particles to a more abstract, yet equally profound kind of symmetry, one that exists not in space, but in the very mathematics that describes energy levels and quantum states. This is the world of spectral symmetry, a concept that uncovers deep, hidden patterns in the musical notes of the universe. In quantum mechanics, the possible energy levels a system can have are known as its spectrum, much like the spectrum of light from a star. These energy levels are the eigenvalues of the system's Hamiltonian operator, the mathematical object that governs its evolution in time. Spectral symmetry is the discovery that these eigenvalues, these allowed energy notes, often arrange themselves in patterns that are far from random. They exhibit breathtaking symmetries, echoing and mirroring each other in ways that point to a deeper, hidden order within the quantum laws. A beautiful and classic example of this can be found in the very atoms that make up our world. Consider the hydrogen atom, the simplest atomic system. Its energy spectrum, the set of allowed energy levels for its single electron, is famously described by the Rydberg formula. The fascinating symmetry here is not in the specific numbers, but in the structure of the energy level diagram itself. The levels are arranged in shells, and transitions between these shells follow strict selection rules that are dictated by the underlying rotational symmetry of the Coulomb force. This symmetry ensures that certain energy transitions are forbidden while others are allowed, creating a pattern of spectral lines that is a direct fingerprint of the atom's spherical symmetry. But the story goes much deeper. In more complex atoms or in the presence of external magnetic fields, these energy levels can split in ways that reveal even more subtle symmetries, known as dynamical symmetries, which explain the intricate patterns we observe in atomic spectroscopy. These aren't just abstract mathematical curiosities. They are the reason we can identify the chemical composition of a star millions of light years away simply by analyzing the symmetric patterns in the light it emits. This principle of spectral symmetry extends far beyond the realm of atomic physics into one of the most extreme environments known to science, the black hole. The study of black hole thermodynamics has revealed a truly astonishing connection. A black hole has entropy, a measure of its hidden information, and this entropy is proportional to the surface area of its event horizon. When physicists began to analyze the quantum vibrational modes on the surface of this horizon, the tiny, flickering fluctuations in its geometry, they discovered something remarkable. The spectrum of these vibrations, the distribution of their energy levels, appears to be statistically identical to the eigenvalue spectrum of a random matrix. This is a profound and unexpected spectral symmetry. It suggests that the quantum mechanics of a black hole horizon is chaotic in a very specific, universal way, and that this chaos is encoded in the symmetric structure of its energy levels. The hidden order within the seemingly random quantum fluctuations of a black hole's surface mirrors the mathematical order found in purely random systems, forging a deep and unexpected link between quantum gravity, thermodynamics, and advanced mathematics. This discovery points toward a grander idea that the spectral symmetry of an object, whether it's an atom or a black hole, might be a fundamental invariant, a unique signature of its underlying physical essence. Two quantum systems that look completely different on the surface, perhaps one describing the vibrations of a string and another describing the interactions of particles, could possess identical or isomorphic eigenvalue spectra. This would mean that despite their vastly different presentations, they are fundamentally the same physical system in disguise, echoing the dualities we explored earlier. The search for these deep spectral connections is more than a theoretical exercise. It is a powerful tool for unifying physics. By recognizing that the same spectral patterns, the same cosmic harmonies, appear in the energy levels of a nucleus, the vibrational modes of a molecule, and the quantum fluctuations of a black hole, we get a tantalizing glimpse of a universal language of nature, written not in forces or particles, but in the symmetric and elegant structure of energy itself. Now, this exploration of symmetry in the spectra of energy levels leads us to a more specific and equally elegant concept, the idea of a physical theory that can look exactly the same even when you perform a dramatic transformation on it. This is the principle of self-duality, a special kind of symmetry where a theory is completely invariant under a duality transformation. It's not just that two different-looking theories describe the same physics. It's that a single theory looks precisely the same when you view it through this transformative lens. The equations are unchanged, the predictions are identical. The theory is a perfect mathematical mirror of itself. Our most profound and established example of this is found in the very theory of light itself. In the pristine emptiness of a vacuum, Maxwell's equations, which govern all of classical electromagnetism, exhibit a stunning and beautiful self-duality. The equations are completely symmetric if you simultaneously swap the electric field for the magnetic field, and the magnetic field for the negative of the electric field. In the absence of any electric charges or currents, there is a perfect democracy between electricity and magnetism. What we call an electric field and what we call a magnetic field are merely labels. The underlying physics does not distinguish between them in a fundamental way. This symmetry is so deep that if you were to suddenly swap all electric and magnetic fields in the universe, Maxwell's equations in vacuum would be utterly unable to tell the difference. This self-duality is the reason why electromagnetic waves can propagate through the void. The changing electric field creates a changing magnetic field, which in turn creates a changing electric field, and so on, in a self-sustaining dance of duality that moves outward at the speed of light. This is more than just a mathematical curiosity. It places incredibly powerful constraints on the form that any theory of electromagnetism can take. Any modification to Maxwell's theory, any attempt to extend it, must respect this sacred self-duality to be considered physically consistent in the vacuum. It acts as a guiding principle, a north star for theorists, ruling out countless alternative proposals that would break this elegant symmetry. This principle extends even into the quantum realm. When we consider the quantum version of electrodynamics, this self-duality manifests in the famous Dirac quantization condition, which we discussed earlier. The product of an electric charge and a magnetic charge must be an integer multiple of a fundamental constant, a result that emerges naturally from the requirement that the quantum theory remain consistent with this underlying classical symmetry. The concept of self-duality extends far beyond electromagnetism, appearing as a crucial feature in some of our most advanced theoretical frameworks. Consider the famous Ising model, a seemingly simple mathematical model used to describe ferromagnetism. On a two-dimensional square lattice, this model is exactly solvable at a specific critical temperature, and it turns out to be self-dual. The model's behavior on the original lattice is exactly mirrored by its behavior on a dual lattice, where the roles of sites and bonds are interchanged. This self-duality is the key that allows physicists to calculate its exact critical exponents, describing how it transitions from a magnetized to a non-magnetized state. It reveals that the model's behavior at this critical point is invariant under a fundamental change of perspective. Perhaps the most significant modern appearance of self-duality is in certain supersymmetric gauge theories, like N=4 super-Yang-Mills theory. This theory is a cornerstone of the AD-S/CFT correspondence and is renowned for its incredible amount of symmetry. It is believed to be exactly self-dual under a transformation that takes the gauge coupling constant to its inverse, a symmetry known as S-duality. When the coupling is weak and particles interact gently, the theory is easy to handle. Astonishingly, S-duality asserts that this weakly coupled description is exactly equivalent to the same theory operating in a regime where the coupling is strong and interactions are fierce and complex. This is a monumental claim. It means that the theory provides its own solution. The difficult, strong coupling physics is not a separate problem, but is simply mapped to an easy, weak coupling version of itself. This self-duality is one of the strongest hints we have that these exotic quantum field theories might be exactly solvable, providing a perfect mathematical window into the heart of strong interactions and quantum gravity through the holographic principle. The presence of such a powerful self-duality suggests that the ultimate laws of the universe might not be complex and arbitrary, but could be founded on principles of such profound and self-referential simplicity that they are their own key to being unlocked. This brings us to a theory that directly confronts the very origin of our universe's large-scale structure, the profound role of hidden symmetry in cosmic inflation. To understand why this is such a revolutionary idea, we need to revisit the two great puzzles of the pre-inflationary cosmos, the horizon problem and the flatness problem. The horizon problem asks why the universe is so incredibly uniform. The cosmic microwave background radiation, the leftover heat from the Big Bang, has the same temperature in all directions to within 1 part in 100,000. But according to the standard Big Bang model, these distant regions of the sky were never in causal contact. There wasn't enough time for light or heat to travel between them to even out the temperature. It's like walking into a vast concert hall and finding that thousands of people who have never spoken to each other are all humming the same note in perfect tune. The flatness problem is just as perplexing. The density of the universe appears to be fine-tuned to an astonishing degree, incredibly close to the critical density that separates a universe that will expand forever from one that will eventually collapse. The odds of this happening by chance in the standard model are astronomically small, like balancing a pencil on its tip for billions of years. The theory of cosmic inflation, first proposed by Alan Guth and others, provides an elegant solution. It posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating by a factor of trillions upon trillions in far less than the blink of an eye. This incredible growth spurt would have stretched a tiny, causally connected patch of space into our entire observable universe, explaining its uniformity. It would also have flattened the cosmic geometry, just as inflating a balloon makes its surface appear flatter and flatter from the perspective of an ant on its surface. But what could possibly power such a monumental event? The answer lies in the hypothetical inflattened field and the hidden symmetries within its potential energy landscape. Think of the inflattened field as a ball sitting at the top of a very flat, very high hill. This hill represents a state of high energy density and negative pressure, the exact conditions needed to drive repulsive gravity and the exponential expansion of inflation. The incredible flatness of this hill, its slow roll potential, is where symmetry enters the picture. This specific shape is not arbitrary. It is often the direct result of an underlying symmetry in the equations governing the inflattened field. This symmetry ensures that the potential is shallow enough for the inflattened to roll down it very, very slowly. During this slow roll, the energy density of the field remains nearly constant, acting like a cosmological constant and fueling the relentless expansion of space itself. Only when the field eventually reaches the steeper part of the potential and rolls into its true minimum does inflation end, converting the energy of the inflattened field into a hot bath of particles in an event called reheating, effectively setting the stage for the standard Big Bang. Different models of inflation propose different origins for this critical symmetry. In chaotic inflation, the symmetry is simple and generic, with a wide class of potentials naturally having the required flatness. In new inflation, the symmetry is more specific, often related to a phase transition where the inflattened field is initially trapped in a false vacuum state, a metastable valley in the potential, due to thermal effects or other corrections. As the universe cools, the symmetry protecting this false vacuum breaks, and the field slowly rolls toward its true, lower energy state. Some of the most compelling models connect the inflattened field to the symmetries of grand unification or even supersymmetry, providing a tangible link between the physics of the incredibly small and the destiny of the entire cosmos. But perhaps the most brilliant consequence of this mechanism is how the quantum seeds for all structure in the universe are sown. The slow roll inflation era is a masterpiece of symmetry, but it is the breaking of that symmetry, or more precisely, the tiny imperfections in it, that creates our world. Due to the quantum uncertainty principle, the inflattened field couldn't be perfectly uniform across space. Tiny quantum fluctuations were inevitable, causing the field to roll down the potential at slightly different rates in different regions. These minuscule variations in the roll-down time translated directly into tiny differences in the energy density of the universe when inflation ended. Regions where the field had rolled slightly further had a little less energy, while regions where it was still higher up had a little more. These quantum jitters, stretched to astronomical sizes by inflation, became the primordial density fluctuations that would later, under the relentless pull of gravity, collapse to form every galaxy, star, and planet we see today. The very same symmetries that made the universe uniform and flat are also responsible, through their subtle and inevitable quantum breakdown, for the beautiful and intricate cosmic structure that defines our existence. The pattern of hot and cold spots in the cosmic microwave background is a direct fossilized imprint of these quantum fluctuations, a snapshot of the hidden symmetry of the inflattened field at a trillionth of a second after the beginning. Yet as profound as the idea of emerging spacetime may be, our journey into the deepest symmetries of the cosmos would be incomplete without paying homage to one of the most visionary and elegant unification attempts in the history of physics, Kaluza-Klein theory. This was a bold, almost magical idea that first revealed how the very geometry of hidden dimensions could be the source of the forces we experience in our everyday world. In the early 20th century, just as Einstein was revolutionizing our understanding of gravity with his general theory of relativity, a little-known German mathematician named Theodor Kaluza performed an act of breathtaking mathematical audacity. He asked a simple yet radical question: what would Einstein's equations look like if we didn't live in a universe of 3 spatial dimensions and 1 time dimension, but in a world with 1 extra spatial dimension? Kaluza took Einstein's famously complex field equations, which describe how matter and energy curve the 4-dimensional fabric of spacetime, and he rewrote them for a 5-dimensional universe. The result was nothing short of miraculous. When he separated out the components of this 5-dimensional gravity, he found that some of the terms described the familiar 4-dimensional gravity of Einstein. But the remaining terms perfectly matched the equations formulated by James Clerk Maxwell for classical electromagnetism. It was as if by merely adding an extra dimension to the universe, the force of electromagnetism simply fell out of the geometry of gravity. The photon, the carrier of the electromagnetic force, emerged naturally from the gravitational field in this higher dimensional space. In one stunning stroke, Kaluza had seemingly unified gravity and electromagnetism, the 2 known fundamental forces at the time, into a single geometric framework. It was a revelation that suggested the deepest laws of physics might not be a collection of separate rules, but different facets of a single, higher dimensional reality. Of course, this immediately raised a glaringly obvious question. If there is a 5th dimension, where is it? Why don't we see it? This is where the Swedish physicist Oskar Klein made his crucial contribution a few years later. He proposed that this extra dimension wasn't like the vast, extended dimensions we move through. Instead, it was curled up into an unimaginably tiny loop, a circle so small that it was completely invisible to any experiment. To understand this, imagine a garden hose stretching off into the distance. From far away, it looks like a simple 1-dimensional line. But if you get very close, you discover it actually has a 2nd dimension, a circular cross-section. Klein suggested that the 5th dimension was similarly compactified, curled up on a scale so minute at the Planck length that it was undetectable. This elegant idea not only solved the problem of the dimension's invisibility, but also provided a beautiful explanation for the quantization of electric charge. In this curled-up dimension, a particle's momentum around the tiny circle would be quantized, and this quantized value turned out to be directly proportional to its electric charge. The discrete nature of charge, a fundamental quantum property, emerged naturally from the topological structure of the hidden dimension. This breathtaking unification comes with a profound implication for the nature of symmetry. The force of electromagnetism is described by a U1 gauge symmetry, a specific kind of local symmetry that governs how the electromagnetic field interacts with charged particles. In the 5-dimensional Kaluza-Klein world, this U1 symmetry is not something added to the theory. It is a direct consequence of the geometric symmetry of the compactified dimension. The circle has a rotational symmetry. You can rotate around it, and its geometry remains unchanged. This is an isometry of the compact space. Kaluza and Klein showed that this isometry of the tiny, curled-up circle directly gives rise to the U1 gauge symmetry of electromagnetism in our 4-dimensional world. In other words, what we perceive as an abstract internal symmetry governing the force of nature is actually the shadow of a very real geometric symmetry of a hidden dimension. The force itself is just the part of higher dimensional gravity that points along this tiny, circular direction. While the original dream of unifying just gravity and electromagnetism was eventually superseded by the discovery of the strong and weak nuclear forces, the core legacy of Kaluza-Klein theory is more powerful today than ever. It established the foundational paradigm that all our fundamental forces, not just electromagnetism, could be understood as the geometric consequence of gravity operating in a higher dimensional spacetime. Modern string theory and M-theory are the direct descendants of this idea, with their 6 or 7 extra dimensions compactified into intricate Calabi-Yau manifolds. The rich isometries of these complex shapes, their own internal geometric symmetries, are what give rise to the full tapestry of gauge symmetries that describe the electromagnetic, weak and strong forces in our world. The standard model of particle physics, with its specific symmetry groups, may ultimately be nothing more than the geometric echo of the particular way the extra dimensions of the universe are curled up. Kaluza-Klein theory was the first brilliant glimpse into this astonishing possibility that the entire universe of forces and particles we inhabit is a four-dimensional shadow play cast by the elegant, symmetric geometry of a higher dimensional reality. But if the symmetries of space-time and forces can emerge from hidden dimensions, then the strange phenomenon of quantum entanglement might be hiding a completely different kind of order. This brings us to one of the most active frontiers of theoretical physics, the search for hidden symmetry in quantum entanglement itself. At first glance, entanglement seems like the ultimate agent of chaos, a spooky, instantaneous connection that defies our classical intuition about separate objects. When two particles become entangled, measuring the state of one instantly determines the state of the other, no matter the distance between them. It's a connection that seems to transcend space, a profound linking of fates that Einstein famously called spooky action at a distance. For decades, this was viewed as a bizarre and almost anti-symmetric disruption of the normal order. But a revolution in perspective is underway, revealing that this spookiness is not random noise. It is the signature of a deep and hidden symmetry structure woven into the fabric of quantum reality. The key to unlocking this structure is a concept from quantum information theory known as entanglement entropy. Think of it this way. If you have a complex quantum system, like a collection of electrons in a solid or the quantum fields of the vacuum itself, you can imagine dividing it into two parts. Part A could be a specific region of space, and Part B could be everything else. Entanglement entropy is a precise measure of how quantumly intertwined or entangled these two parts are. It quantifies the information about Part A that is hidden and inaccessible without also knowing about Part B. In most everyday systems, this entanglement entropy is extensive. It grows in proportion to the volume of the region you're looking at, just as you'd expect. But physicists began to discover something astonishing in certain exotic states of matter. The entanglement entropy didn't scale with the volume. Instead, it scaled with the area of the boundary separating the two regions. This area law for entanglement entropy is a monumental clue. It's a direct echo of the holographic principle we encountered earlier, where the information in a volume is bound by its surface area. This geometric constraint on quantum information points directly toward a hidden symmetry. It suggests that the intricate web of entanglement connecting particles within a region is not arbitrary. It is organized in a highly symmetric way that respects the geometry of the boundary. The entanglement pattern itself becomes a fingerprint of a deeper order. This is where topology enters the picture. Topology is the branch of mathematics concerned with properties that remain unchanged under continuous deformations, stretching, bending, or twisting, but not tearing. A coffee mug and a donut are topologically equivalent to a mathematician because one can be smoothly deformed into the other. In certain quantum materials, known as topological phases of matter, the ground state of the entire system possesses a global entanglement structure that is topologically protected. This means that the pattern of entanglement and the exotic particles that arise from it are incredibly robust. They are immune to local disturbances, imperfections, or minor changes in the environment. You can poke and prod the material, but as long as you don't fundamentally tear its quantum fabric, this entangled state and its properties persist. This robustness is a direct manifestation of a hidden symmetry. The laws governing the system have a topological symmetry. They are invariant under any smooth deformation of the material's geometry. This symmetry isn't about rotating a shape. It's about preserving the essential global connectivity of the quantum information. The most famous examples of this are fractional quantum Hall states, observed in two-dimensional electron gases subjected to powerful magnetic fields. In these systems, electrons become entangled in such a unique way that they give rise to quasiparticles with fractional electric charge. Even more astonishingly, some of these quasiparticles are anyons, which are neither bosons nor fermions. When two anyons are swapped, their quantum wave function acquires a phase factor that is neither 1 nor -1, but a complex fraction. This bizarre behavior is entirely dictated by the topological symmetry of the entangled state they live in. The hidden symmetry of the entanglement pattern directly determines the types of particles that can exist. This profound connection is revolutionizing our understanding of the vacuum of spacetime itself. According to the principles of quantum field theory, the vacuum is not an empty void. It is a seething, bubbling soup of virtual particles constantly flashing in and out of existence. These quantum fluctuations are entangled with each other in a specific, intricate pattern. This vacuum entanglement is now believed to be the very glue that holds spacetime together. The smooth, continuous geometry we experience might be an emergent property of this underlying network of quantum connections. The hidden symmetries within this entanglement network could be the ultimate source of the symmetries we see in the laws of physics. A local disturbance that breaks entanglement could manifest as a distortion in spacetime, what we perceive as gravity. In this breathtaking view, the search for a theory of quantum gravity becomes the search for the symmetries of quantum information. The universe may not be written in the language of particles and forces, but in the language of entanglement, with its own hidden, topological symmetries defining the rules of existence. Now, let's shift our focus from the quantum realm of entanglement to a different, yet equally profound application of symmetry, one that uses the very constraints of symmetry to essentially solve the universe. This is the powerful and elegant framework known as the conformal bootstrap. The name itself is a fascinating clue. Conformal refers to the scale and angle-preserving symmetry we discussed earlier, and bootstrap evokes the almost unbelievable idea of pulling oneself up by one's own bootstraps. In physics, it describes a method where a theory is defined and solved entirely by its own self-consistency, with no external input. It's a program that uses the immense power of symmetry, not just as a property of a theory, but as the very tool to build that theory from the ground up. The core philosophy is as ambitious as it is simple. Instead of starting with a specific equation or a Lagrangian and then discovering its symmetries, the conformal bootstrap starts by imposing symmetry as a non-negotiable requirement. It asks if we demand that a physical theory is perfectly conformally symmetric, that its laws are invariant under transformations that preserve angles but can stretch and shrink distances, what must that theory look like? What are the absolute, unavoidable constraints that this majestic symmetry places on how particles can interact? The answers to these questions are found in the correlation functions, which are mathematical objects that essentially tell us how likely different particles are to be found in relation to one another. In a conformal field theory, these functions are not arbitrary. Their form is almost completely locked in by the symmetry. The conformal bootstrap is the process of exploiting these constraints to their absolute limit. The process works by writing down a fundamental equation of self-consistency known as the crossing equation. Imagine a simple interaction between four particles. There are different ways or channels to calculate the outcome of this interaction. You could group particles 1 and 2 together and consider how they interact with particles 3 and 4. Or you could group 1 and 4 together and consider their interaction with 2 and 3. The profound physical requirement is that no matter which mathematical path you take to calculate this single event, you must always get the exact same answer. Reality has to be consistent with itself. The crossing equation is a formal expression of this seemingly obvious fact. But when you combine this requirement with the incredibly rigid structure imposed by conformal symmetry, it becomes an equation of immense power. It tightly binds together the properties of all the particles in the theory, their scaling dimensions which define how they behave under zooming in or out, and their operator product expansion coefficients which define how they combine. What makes this approach so revolutionary is that it is non-perturbative. Traditional methods in physics often rely on approximations, like starting with a simple interaction and then adding small corrections. The bootstrap makes no such approximations. It treats the theory exactly, using the full, non-linear constraints of symmetry and self-consistency. Researchers implement this by using numerical methods to analyze the crossing equation. They systematically search the vast theory space of all possible scaling dimensions and interaction strengths, and they ruthlessly rule out any combination of values that would violate the crossing equation. It's a process of elimination on a cosmic scale, carving away huge swaths of mathematical possibility to isolate the tiny islands that correspond to physically consistent universes. The result is not a derivation from first principles, but a discovery of what first principles must be. This method has scored spectacular successes, most notably in determining the critical exponents of the iconic three-dimensional Ising model. This model describes the precise point where a material loses its magnetization as it heats up, a phase transition with profound conformal symmetry. For decades, physicists calculated these exponents using various approximation techniques, arriving at values that were close but not perfectly agreed upon. The conformal bootstrap analyzed the crossing equations for this system with incredible numerical precision, and it produced values for these exponents that are now considered definitive. It achieved an accuracy that surpassed all other methods, providing a stunningly precise map of this conformal universe's laws purely from the requirement of consistency. This success has cemented the bootstrap as a premier tool for studying critical phenomena, proving that symmetry and self-consistency alone can be enough to unlock the deepest secrets of nature's most delicate transitions. Now, after exploring the symmetries that may govern the very fabric of space-time and the genesis of the cosmos, we turn our attention to one of the most enigmatic and ghostly particles in existence, the neutrino. These elusive entities, so light they were long thought to be massless, so reluctant to interact that trillions pass through your body every second without a trace, hold a secret that is rewriting the textbooks of particle physics. The key to this secret is a bizarre and beautiful quantum phenomenon known as neutrino oscillation, and many theorists believe it is the clearest signpost we have pointing toward a deeply hidden symmetry operating within the family of particles known as leptons. This story begins with a mystery that plagued physicists for decades, the solar neutrino problem. Our sun, powered by nuclear fusion, should produce a specific, calculable number of electron neutrinos. Yet experiments on Earth, most famously the Homestake mine detector, consistently measured only about a third of the predicted flux. The resolution to this puzzle was as shocking as it was elegant. Neutrinos, it turns out, are not static entities. They are quantum chameleons. An electron neutrino produced in the heart of the Sun does not necessarily arrive at Earth as an electron neutrino. During its journey, it can transform or oscillate into a muon neutrino or a tau neutrino. This incredible process of neutrino oscillation provided irrefutable proof that neutrinos have mass, a finding that was so revolutionary it earned the Nobel Prize in Physics in 2015. But why do they oscillate? The mechanism is a masterpiece of quantum mechanics, and it hinges on a profound mismatch. The particles that participate in the weak nuclear force, the ones that are produced and detected in interactions, are not the same as the particles that propagate through space with a definite mass. Physicists call the former flavor eigenstates electron, muon, tau, and the latter mass eigenstates neutrino 1, neutrino 2, neutrino 3. These two sets of states are related by a transformation matrix, a mathematical object that is the heart of the mystery. The fact that this matrix exists, that the flavor and mass states are not aligned, is what allows a neutrino to change its identity as it travels. The oscillation pattern, how often and how completely the neutrinos swap flavors, is dictated by the differences in the squares of their masses and by the specific angles and phases within this transformation matrix, known as the Pontecorvo-Maki-Nakagawa-Sakata matrix or Piermanès matrix. When experimentalists finally pinned down the values of these mixing angles, they were met with another surprise. Two of the angles are large, one of them being nearly 45 degrees. This is radically different from the analogous matrix for quarks, where all the mixing angles are small. A 45-degree angle is highly suggestive. In the language of symmetry, it often points toward a specific, maximal kind of mixing. It hints that there might be a fundamental symmetry operating in the lepton sector that treats the muon and tau neutrino flavors as nearly indistinguishable, or that relates them in a very symmetric way. This is where the search for a hidden symmetry begins in earnest. One compelling proposal is the concept of mu-tau symmetry. This is a simple, elegant idea that the laws of physics might be approximately symmetric if we were to swap every muon neutrino with a tau neutrino. In a world with perfect mu-tau symmetry, the mixing angle θ23 would be exactly 45 degrees, and a certain complex phase, which could be the source of matter-antimatter asymmetry in the leptonic sector, would be exactly 90 degrees. Our real world is not perfect. Experiments show slight deviations from these ideal values, but this is precisely what makes the idea so powerful. The fact that the data gets so close to these symmetric values suggests that mu-tau symmetry might be a fundamental property of the underlying theory that is broken only slightly, perhaps by the same mechanism that gives the muon and tau leptons their very different masses. The symmetry is hidden in the high-energy regime and only reveals itself through these tantalizingly almost perfect numbers we measure at low energies. To explain this, physicists look to grander frameworks, often incorporating the seesaw mechanism. This brilliant idea posits that the tiny masses of the neutrinos we observe are a direct consequence of the existence of extremely heavy, sterile neutrinos particles that do not feel the weak force. The light neutrino mass is inversely proportional to the mass of these heavy partners. Crucially, the structure of the mass matrix that governs all neutrinos could possess a high degree of symmetry at a grand unification scale. This symmetry would then be broken as the universe cools, but its fragments would remain imprinted on the low-energy effective theory, manifesting as the specific patterns we see in the Piermanès matrix. Models based on discrete symmetry groups like a 4 or S4, the symmetry groups of the tetrahedron and the cube, respectively, are particularly popular. In these models, the lepton fields are arranged into specific representations of these geometric symmetry groups. The dynamics of the theory then force the mass matrices to take a very particular form, one that naturally predicts large mixing angles, providing a beautiful and testable origin story for the hidden symmetry behind neutrino oscillations. The ongoing, painstaking measurements of neutrino parameters are thus a direct probe into this potential symmetric origin, a way to reverse engineer the fundamental laws that governed particles in the earliest moments of the universe. Yet this elegant interplay between order and disorder, between the microscopic and the macroscopic, finds one of its most profound expressions not in the exotic realms of quantum gravity, but in the seemingly straightforward study of how large collections of particles behave. This is the domain of statistical mechanics, a branch of physics that bridges the chaotic dance of individual atoms with the predictable properties of the materials they form. And hidden within its mathematical heart lies a stunning class of symmetries that are not about rotations or reflections, but about the very equivalence of different physical realities. These are the dualities of statistical mechanics, and they provide some of the most powerful tools we have for unraveling the universe's deepest secrets. To understand the sheer power of these dualities, we can look to one of the most celebrated models in all of physics, the Ising model. Conceived in the 1920s to explain ferromagnetism, it imagines a universe in a grid where each site holds a simple magnetic arrow or spin that can point either up or down. Each spin interacts with its immediate neighbors, wanting to align with them to lower the energy of the system, while the ambient heat provides random kicks that try to disrupt this order. This creates an eternal tug of war between energy and entropy, between the drive for order and the tendency toward chaos. The question the model asks is deceptively simple. Under what conditions does the collective will for alignment win out, causing the entire grid to spontaneously magnetize? The point where this happens is the critical temperature, a phase transition as fundamental to physics as the freezing of water. Solving the Ising model in 2 dimensions was a Herculean task, first achieved by Lars Onsager in 1944. His solution was a masterpiece of mathematical physics, revealing that at the critical temperature, the system becomes scale invariant. It looks the same at every level of magnification, a fractal dance of ordered and disordered regions. But the true magic, the hidden symmetry, was revealed through a transformation now known as the Kramers-Wanya duality. This duality constructs a radical new perspective. It takes the original model, defined on the sites of the grid, and maps it exactly onto a new model defined on the bonds between those sites. In this dual picture, the roles of high temperature and low temperature are swapped. The fierce struggle for order at low temperatures in the original model is perfectly mirrored by the frenetic chaos of high temperatures in the dual model, and vice versa. This duality provided the first key insight into the exact location of the critical point. It is the special self-dual temperature where the model looks exactly the same from both perspectives. It was a revelation that 2 completely different-looking physical descriptions could be 2 sides of the very same coin. This breakthrough was merely the beginning. The principle of duality expanded far beyond the simple Ising model into the rich landscape of lattice gauge theories. These theories are the mathematical backbone of our understanding of the strong nuclear force, the glue that holds quarks together inside protons and neutrons. Here, the fundamental elements are not simple spins on a grid, but more abstract variables associated with the links between grid points. These represent the force fields themselves. The physics is about the interplay between these links, and the models can be incredibly difficult to solve due to the intense strength of the interactions. This is the infamous problem of strong coupling. Yet, once again, duality provides a master key. For a wide class of these gauge theories, there exists a profound duality that maps a strongly coupled gauge theory onto a weakly coupled theory. It's as if you're given a locked, impregnable safe. Instead of trying to break it open, duality gives you a magical blueprint that shows this safe is identical to a simple, unlocked wooden box. You simply study the easy box to learn everything about the impossible safe. The most famous example of this is the duality between the 3-dimensional Ising model and a specific gauge theory in 4 dimensions. This connection is not just a mathematical curiosity. It's a practical bridge that allows physicists to transport results from a well-understood system to a poorly understood one. By solving the Ising model, we can learn profound truths about the confining phase of gauge theories, the state where quarks are forever bound and cannot be isolated. This is the power of duality. It reveals a hidden symmetry of nature that is not about the geometry of space, but about the equivalence of different physical descriptions. It tells us that our choice of variables, whether we describe a system in terms of spins, bonds, or gauge fields, is not fundamental. The underlying physics is invariant, and this invariance is a symmetry more deep and abstract than any we have encountered before. These discoveries culminate in an idea that connects back to the very quantum nature of spacetime, the notion of gauge-gravity duality, with the AD/S/CFT correspondence as its prime example. While this is often discussed in the context of string theory, its foundation is deeply rooted in the dualities of statistical mechanics. It proposes that a gravitational theory in a warped anti-de Sitter space is completely equivalent to a conformal field theory, a special kind of quantum system with scale symmetry living on its boundary. This is the ultimate expression of the duality principle. It connects a theory with gravity to a theory without it. It translates the mysterious quantum gravitational physics of black holes in the bulk into the complex, but non-gravitational thermodynamics of a hot, dense plasma on the boundary. Problems that are utterly intractable in one description become elegantly simple in the other. The holographic principle, which once seemed like a bizarre feature of black holes, is revealed by this duality to be a fundamental and general property of quantum gravity. The hidden symmetry uncovered in the dualities of statistical mechanics, the equivalence of different descriptions, thus becomes one of our most powerful guides to understanding the universe at its most fundamental level, suggesting that the true nature of reality might be described by a network of interconnected dual theories, each offering a unique window into the same underlying truth. But if symmetries govern the formation of structure and the behavior of particles, they also reign supreme in the most extreme objects in the cosmos, black holes. These gravitational monsters, often portrayed as the ultimate agents of chaos and destruction, are in fact paragons of order and simplicity when viewed through the lens of fundamental physics. This remarkable simplicity is encapsulated in one of the most elegant ideas in general relativity, the no-hair theorem. The theorem's poetic name suggests that a black hole, once it has settled down, has no distinguishing features, no hair, no intricate styling. It is completely bald, characterized by just three, and only three, numbers: its mass, its electric charge, and its angular momentum or spin. Imagine two black holes, one formed from the collapse of a massive star and another from the merger of two dense neutron stars. After the incredible violence of their formation subsides, after all the gravitational waves have rippled out into the universe, these two black holes become utterly indistinguishable if their mass, charge, and spin are identical. Every other detail, what kind of star made them, whether they swallowed planets or pure energy, if they were made of matter or antimatter, is entirely erased, lost forever behind the event horizon. The black hole embodies a profound and almost terrifying symmetry. It is the ultimate simplifier, reducing the complex, messy history of everything that fell into it down to three simple, measurable quantities. This incredible simplicity is a direct consequence of the symmetries inherent in Einstein's equations themselves. The equations of general relativity are diffeomorphism invariant, meaning that the laws of physics remain the same regardless of how you choose to label your coordinates in spacetime. This is a powerful form of symmetry that severely restricts the kinds of stable solutions the equations can have. The no-hair theorem is the manifestation of this restriction for black holes. It tells us that any hair, any additional field or complex structure you might try to attach to a black hole, whether it's a remnant of a magnetic field or some exotic quantum number, will either radiate away during the formation process or simply not be supported by the stable black hole solution. The black hole's event horizon acts as a cosmic sensor, hiding all the details and presenting to the outside universe a perfectly smooth, symmetric, and information-poor surface. This is the classical picture, a universe where black holes are the simplest objects imaginable. Yet, this perfect symmetry creates one of the most famous paradoxes in modern physics. If a black hole has no hair, then what happens to the information contained in the objects that formed it? According to quantum mechanics, information cannot be destroyed, it can only be scrambled. Throwing a perfectly detailed encyclopedia into a black hole would seem to violate this sacred principle if the black hole only remembers the book's total mass and not a single word. This tension between the symmetric, information-erasing black hole of general relativity and the information-preserving requirement of quantum mechanics is the heart of the black hole information paradox. It suggests that our classical understanding of black hole symmetry must break down, and that a deeper quantum description must reveal a more subtle form of order. That deeper order may lie in the quantum properties of the event horizon itself. When we examine the horizon not as a classical boundary but through the lens of quantum field theory, we find it is not a barren, empty surface. Due to the immense gravitational field, the vacuum of spacetime near the horizon is teeming with activity. Virtual particle pairs constantly flicker into existence. Normally, these pairs annihilate each other almost instantly, but at the event horizon, one particle can fall in while the other escapes, appearing to an outside observer as a faint glow of radiation, the famous Hawking radiation. This process slowly evaporates the black hole over astronomical timescales. The incredible discovery was that the spectrum of this radiation, the distribution of its energy, is exactly thermal. It looks precisely like the radiation emitted by a perfect blackbody, an object in perfect thermal equilibrium. This thermal character is itself a signature of a hidden symmetry. A black hole has a temperature, and its radiation is featureless and random, containing no information about what fell in. It is the ultimate symmetric emission, but the plot thickens when we consider the quantum geometry of the horizon. The mathematics describing the low-energy physics near a black hole's event horizon exhibit a powerful conformal symmetry in 2 dimensions. This means the physics looks the same under transformations that stretch and shrink distances but preserve angles. This 2-dimensional symmetry, emerging from the physics of a 3-dimensional object, is a crucial clue. It suggests that the horizon's microscopic degrees of freedom, the quantum bits that ultimately store the black hole's information, might be organized in a way that is governed by a 2-dimensional conformal field theory. This is a direct and stunning link to the holographic principle and the AD/S/CFT correspondence we discussed earlier. The black hole's entropy, which is proportional to its horizon's area, is now understood as a measure of the number of these microscopic quantum states on the horizon's surface. The information isn't truly lost. It is believed to be encoded on this 2-dimensional surface in a massively scrambled holographic form, and it is slowly leaked back out into the universe in the subtle correlations between the particles of Hawking radiation. This perspective transforms the black hole from a simple, symmetric object into the most complex and densely packed information storage system in the universe. The perfect classical symmetry of the no-hair theorem gives way to a rich quantum mechanical symmetry of its microscopic constituents. The event horizon is not a smooth, featureless null surface, but a vibrant, fluctuating quantum structure with an immense amount of hidden information, all organized according to deep symmetries that we are only beginning to understand. The study of black holes is no longer just about gravity. It is a gateway into the fundamental principles of quantum information, thermodynamics, and the hidden symmetries that may one day unite them all into a complete theory of quantum gravity. We have journeyed through symmetries that define particles, govern forces, and perhaps even weave the fabric of spacetime itself. But there is one final, pivotal piece of the puzzle, a concept so powerful it answers a deceptively simple question. If the laws of the universe are founded on such beautiful symmetry, why does our world look so manifestly asymmetric? Why are particles heavy? Why do forces have different strengths? And why does anything have substance at all? The answer lies in a profound and elegant process known as spontaneous symmetry breaking. This is the mechanism by which a perfectly symmetric state becomes unstable, and the system spontaneously chooses a less symmetric but stable reality. It is the universe's way of hiding its true symmetric nature, leaving behind only clues for us to find. To grasp this, imagine a perfectly sharp pencil balanced on its point. The situation is exquisitely symmetric. From a bird's eye view, the pencil looks the same if you rotate your perspective. Every direction is equivalent. But this perfect symmetry is also profoundly unstable. The slightest breath of air, the smallest vibration, will cause the pencil to tip over and fall onto its side. In doing so, it chooses a specific direction. The symmetry of the upright state is broken. Crucially, the laws of physics governing the pencil gravity, the nature of the table, are still perfectly symmetric. There was no preferred direction in the rules. The asymmetry is not in the laws, but in the solution, in the state that the system settled into. The pencil had many possible states it could fall into, all equally valid from the perspective of the symmetric laws, but it randomly selected just one. This is the essence of spontaneous symmetry breaking, symmetric laws giving rise to asymmetric realities. In the realm of particle physics, this abstract idea becomes the engine that gives mass to the universe. The pivotal character in this drama is the Higgs field. Imagine this field not as a pencil, but as a vast, invisible ocean filling all of space. In its high-energy, symmetric state, like the pencil standing upright, the value of the Higgs field is zero everywhere. But this state is unstable. Just as the pencil falls, the Higgs field falls into a stable state where its value is not zero, but some constant everywhere. This is its new, stable ground state, its lowest energy configuration. However, there isn't just one way for this to happen. The potential energy landscape of the Higgs field, often depicted as a Mexican hat or sombrero shape, has a high, unstable peak at the center, the symmetric state, and a continuous circular valley all around it. The field must choose a single point in that valley to settle into. In making that choice, it picks a specific direction, breaking the original rotational symmetry of the potential. This is where the magic happens for other particles. As particles like electrons and quarks travel through the universe, they interact with this non-zero Higgs background field that permeates everything. Some particles interact with it very strongly. Imagine a celebrity trying to walk through a crowded party. Their progress is slowed by constant handshakes and conversations. They acquire a kind of social inertia, making them massive and slow to accelerate. A W boson, which carries the weak nuclear force, is like that celebrity. It interacts so strongly with the Higgs field that it becomes very heavy. Other particles, like photons, are like a stranger who slips through the crowd unnoticed. They don't interact with the Higgs field at all and thus remain massless, forever zipping at the speed of light. The Higgs mechanism is this process. The breaking of the field's symmetry provides a universal drag, converting raw interaction strength into the physical property we experience as mass. The mass of every fundamental particle is not an innate property, but a measure of how strongly it couples to this cosmic Higgs field background. The beauty of this mechanism is that it hides the universe's true symmetry, only revealing it when we provide enough energy. If we could heat the universe back up to trillions of degrees, like it was just after the Big Bang, we would add enough energy to lift the Higgs field back up to the top of the Mexican hat, restoring the symmetric state where the field's value is zero. In that extreme environment, the symmetry would be restored, the Higgs drag would vanish, and particles like the W and Z bosons would become massless, just like the photon. The different forces would begin to look more similar, hinting at a deeper unity. The symmetries we've been searching for are therefore not gone. They are simply hidden, spontaneously broken by the cooling of the cosmos. They are the true, fundamental laws, and the asymmetric world we see is just the frozen, low-energy remnant of that more perfect and symmetric beginning. Now, let's descend from the cosmic scale of black holes and Higgs fields and journey into a realm where profound symmetry emerges not from the vacuum of space, but from the intricate world of electrons confined to a flatland. This is the quantum Hall effect, a phenomenon so rich and bizarre that it has become one of the most fertile grounds for discovering new physics, and it all begins with a simple experiment. Imagine taking a super clean, two-dimensional sheet of semiconducting material, like a layer of electrons trapped at the interface of two different crystals. Then you cool this system down to within a few degrees of absolute zero and place it in an incredibly powerful magnetic field, millions of times stronger than Earth's. What happens next is not just a minor curiosity. It's a display of quantum magic that reveals a hidden architecture of reality. As you gradually increase the strength of the magnetic field perpendicular to this electron sheet, you measure the electrical resistance across the sample. In an ordinary three-dimensional wire, resistance changes smoothly. But here, in this two-dimensional quantum world, the data reveals a breathtaking staircase. The resistance across the sample, known as the Hall resistance, doesn't change gradually. Instead, it forms perfectly flat plateaus where it remains constant over a range of magnetic field strengths and then jumps sharply to the next plateau. The most astonishing part is the values of these plateaus. They are quantized with unimaginable precision to fractions defined by fundamental constants. The resistance on a plateau is exactly the Planck constant divided by the square of the electron charge, times 1 over an integer, 1, 2, 3, and so on. This isn't just accurate to a few decimal places. It is one of the most precisely measured quantities in all of physics, reproducible to within 1 part in a billion. This is the integer quantum Hall effect, and its stunning precision is the first clue that a deep, hidden symmetry is at work, locking these values into place with mathematical perfection. The explanation for this bizarre behavior forces us to abandon classical intuition entirely. The powerful magnetic field constrains the electrons to move in circular orbits, known as cyclotron orbits. Quantum mechanics then dictates that the energy levels available to these orbiting electrons are not a continuous ladder but a set of discrete, equally spaced steps called Landau levels. The strength of the magnetic field determines how many electrons can fit into each Landau level. When a Landau level is exactly filled, the system enters a special, incompressible quantum state. It's as if the entire two-dimensional electron sea freezes into a single, unified quantum object. In this state, the electrons cannot move easily to conduct electricity within the sample, which is why the resistance along the current flow becomes zero, a state of superconductivity. But the resistance across the current, the Hall resistance, becomes locked onto one of those precise fractional values. The robustness of this state and the perfection of the quantization is protected by a hidden symmetry that emerges from the collective behavior of all the electrons together. It's a symmetry that is not present in the individual particles but arises from their tangled quantum interactions, making the system immune to disorder, impurities, or minor imperfections in the material. This is the hallmark of a topological phase of matter, where the global, holistic properties of the system are what matter, not the local details. The plot thickens dramatically when we make the system even more exotic. If you achieve even purer samples and stronger magnetic fields, a fractional version of the effect emerges. Here, the resistance plateaus appear at fractional values like 1/3, 2/5, or 3/7. This is the fractional quantum Hall effect, and it is even more mysterious. It implies that the electrons are no longer acting as individual particles. The immense magnetic field and their strong mutual repulsion force them to organize into a new, emergent quantum fluid. In this state, the fundamental excitations are not electrons. They are quasi-particles that carry only a fraction of the electron's charge, like 1/3 or 1/5. Even more bizarrely, these quasi-particles are enyons, a type of particle that exists only in 2 dimensions and defies the standard classification of fermions and bosons. When 2 enyons are slowly swapped around each other, their quantum wave function doesn't just pick up a simple plus or minus sign. It acquires a complex phase factor, a fractional rotation in the complex plane that has no analog in our 3-dimensional world. This exotic statistics is a direct manifestation of a deep topological symmetry. The behavior of the particles depends not on the exact path they take, but on the general topology of how they braid around one another. The quantum Hall system is essentially performing a continuous, intricate ballet where the dancers' identities are defined by their collective motion. This leads us to the profound symmetries and dualities that make the quantum Hall effect a theoretical playground. One of the most beautiful is particle-Hall symmetry. In the quantum Hall system, this is not just a vague concept, it is an exact, emergent duality. It states that the physics of a system with a certain number of electrons filling a Landau level is exactly equivalent to the physics of a system based on the holes, the absences of electrons in that same level. For every description in terms of electrons, there is a perfect mirror description in terms of holes. This symmetry is so powerful that it tightly constrains the possible values the Hall resistance can take, forcing them to be precisely quantized. It reveals that what we call an electron and what we call a hole are not fundamental opposites but are dual descriptions of the same underlying quantum reality, much like the electric-magnetic duality we explored earlier. Furthermore, different quantum Hall states characterized by different fractions are often connected by a web of dualities. A state at one filling fraction might be mathematically mapped onto a state at a different fraction through a transformation that swaps strong coupling for weak coupling, making an intractable problem suddenly solvable. This is reminiscent of the dualities in string theory and gauge theories, but it is happening in a humble, human-made semiconductor chip sitting in a lab at near absolute zero. The fact that the same mathematical structures appear in the quest for quantum gravity and in the behavior of electrons in a magnetic field is a stunning hint of a universal language of symmetry running through all of physics. The ultimate significance of the quantum Hall effect is that it provides a tangible, experimental window into the power of topological order. This is a new kind of order that cannot be described by the traditional Landau paradigm of symmetry breaking, where order is defined by a local order parameter. Topological order is a global property. It is encoded in the long-range quantum entanglement patterns between electrons spread across the entire sample. This entanglement is what makes the system so robust and what gives rise to the exotic enyonic quasiparticles. The quantum Hall effect taught us that matter can exist in entirely new phases, phases that were not dreamed of in conventional physics, and that these phases are protected and defined by hidden symmetries emerging from the quantum information itself. By studying this intricate dance of electrons in a flatland, we are not just learning about condensed matter physics, we are uncovering fundamental principles about how complexity and order can emerge from simplicity, principles that may eventually illuminate the deepest mysteries of the cosmos itself. But if the quantum Hall effect reveals profound order in a 2-dimensional plane, what about the fundamental nature of our 4-dimensional spacetime? This brings us to a theory that is as beautiful as it is radical, a framework that completely reimagines the very building blocks of reality. This is twistor theory, the brainchild of the legendary physicist and mathematician Roger Penrose. It proposes a stunning and hidden symmetry where the points of spacetime are not fundamental. Instead, they are secondary constructions that emerge from a more primary, deeply symmetrical reality, the world of twistors. To grasp this monumental shift in perspective, we need to start with the geometry of light. In our conventional view of spacetime, a point is defined by where and when an event occurs a set of 4 coordinates. Penrose asked a revolutionary question: What if these points are not the true atoms of the universe? What if the most fundamental entities are actually the paths of light rays themselves? Imagine a single photon, a particle of light zipping through the void. Its entire existence is defined by its direction and its energy. In twistor theory, the mathematical description of this light ray is a twistor. A twistor is not a point in space-time. It is an object that naturally encodes both where the light ray is and what its momentum is. It's a unified description of the light ray's geometry and its dynamics all wrapped into one. The magic of this approach is its inherent symmetry. Our standard description of spacetime, even in Einstein's theory of relativity, has a fixed, rigid structure. But twistor space, the space where all these twistors live, is born with a beautiful property known as conformal symmetry built right into its DNA. Remember, conformal symmetry is about preserving angles while allowing distances to stretch and shrink. Twistor theory doesn't need to add this symmetry later. It's the natural default state of this alternative universe of description. This makes it incredibly powerful for describing massless particles like photons and gravitons, whose physics is inherently conformally symmetric. So how do we get from this abstract twistor space back to the familiar spacetime we experience? This is where Penrose's theory reveals its true elegance. A point in our ordinary spacetime is not a fundamental object in twistor theory. Instead, a point is defined by all the light rays that pass through it. Think of a single point in a dark room. How would you define it? You could shine countless beams of light through it from every possible direction. That point is the intersection of all those beams. In twistor theory, that collection of light rays, each described by a twistor, defines the spacetime point. Our entire four-dimensional universe, with its rich geometry, is reconstructed from the interrelationships between these more fundamental twistor objects. Spacetime is not the stage, it is a performance that emerges from the dance of twistors. This reversal of perspective making light rays more fundamental than points has profound advantages. Many of the complex equations of physics, particularly those describing massless fields and their interactions, become dramatically simpler when translated into the language of twistor space. Problems that are notoriously difficult in conventional spacetime can sometimes be solved with elegant geometry in the twistor picture. It's like trying to solve a complicated algebra problem and then discovering that if you view it as a shape, the answer becomes immediately obvious. Furthermore, the notorious infinities that plague quantum field theory, which require the awkward process of renormalization to remove, often simply don't appear in the twistor formulation. The built-in conformal symmetry of the twistor world seems to naturally suppress these mathematical pathologies, suggesting it might be a cleaner route to uniting quantum mechanics with general relativity. Perhaps the most ambitious hope for twistor theory is its potential to illuminate the quantum nature of spacetime itself. In the twistor view, the fuzzy, non-commutative geometry expected at the Planck scale, where the concept of a definite point in spacetime breaks down, might find a very natural description. If spacetime points are not real but are emergent from the relationships of twistors, then the quantum uncertainty of those relationships could directly lead to a granularity of spacetime. The dream is that twistor theory could provide a purely geometric foundation for quantum mechanics, where probabilities arise not from abstract axioms, but from the complex geometry of twistor space. For decades, it was a niche but deeply admired corner of theoretical physics. However, its influence has exploded in recent years due to a stunning and unexpected connection. It turns out that twistor theory provides the most powerful known mathematical tool for calculating scattering amplitudes in certain quantum field theories. Scattering amplitudes are the probabilities for particles to collide and transform into other particles, the core calculable outcomes of experiments at places like the Large Hadron Collider. These calculations, using traditional Feynman diagram techniques, can involve thousands of immensely complicated integrals. but physicists discovered that these same amplitudes for certain theories can be described with breathtaking simplicity and beauty in the language of twistors. The answers can be written down in just a few lines, revealing hidden patterns and symmetries that were completely invisible in the standard approach. This has revolutionized the field of amplitude calculations, turning a domain of brute force algebra into one of elegant geometry. This practical success has validated Penrose's visionary intuition, proving that twistors are not just a beautiful mathematical abstraction. They offer a genuinely powerful new way to compute the behavior of the real world, strongly hinting that they are indeed pointing toward a deeper layer of cosmic symmetry. But if the symmetries that govern our universe are to be found anywhere, they are written in its oldest and most sacred text, the cosmic microwave background radiation. This is the faint, cold glow that fills the entire sky, the cooled and stretched remnant of the hot, dense plasma that made up the infant universe just 380,000 years after the Big Bang. For cosmologists, this is not just ancient light. It is a detailed baby picture of the cosmos, a snapshot of the universe in its infancy, and it is within the subtle statistical patterns of this light that we search for the fingerprints of the universe's deepest and most hidden symmetries. When we look at a full sky map of this radiation, the first thing that strikes us is its incredible uniformity. The temperature is almost exactly the same in every direction, varying by only about 1 part in 100,000. This overwhelming smoothness is the most dramatic evidence for the inflationary period we discussed earlier, a time when a microscopic patch of the universe was stretched to become larger than our entire observable horizon. This process would have ironed out any initial irregularities, leaving behind a universe that is, on the largest scales, statistically isotropic and homogeneous. This means that there are no special places or preferred directions in space. The universe looks the same everywhere and in every direction, a profound symmetry that forms the foundational principle of modern cosmology, known as the cosmological principle. Yet, when we examine this map with exquisitely sensitive instruments like the Planck satellite, we begin to see tiny, frozen ripples in the temperature. These fluctuations are the seeds of all future structure. The galaxies and clusters we see today grew from these minute density variations under the relentless pull of gravity. The standard cosmological model makes a very specific prediction about the statistical nature of these fluctuations. It predicts that they should be Gaussian and random, like the static on an old television set, and that they should be statistically isotropic, meaning their statistical properties should be identical no matter which direction you look. This would be the ultimate signature of a universe born from a perfectly symmetric, quantum-driven process like inflation. But here is where the plot thickens, and where the search for hidden symmetry takes a fascinating turn. As our measurements have become more and more precise, several persistent and puzzling anomalies have emerged, features in the data that subtly but stubbornly defy the predictions of perfect statistical isotropy. For instance, the fluctuations on one side of the sky appear to be slightly larger on average than on the other side, a feature known as the hemispherical power asymmetry. It's as if the universe has a preferred axis, a mysterious lopsidedness that challenges our assumption of a perfectly symmetric origin. Another famous anomaly is the cold spot, a surprisingly large and unusually cold region in the southern galactic hemisphere that is far larger and colder than the standard model can easily accommodate. Could these be mere statistical flukes, the cosmic equivalent of rolling a die and getting a 6-10 times in a row? Or are they the first tantalizing clues of a deeper, hidden structure imprinted on the universe at its birth? One compelling possibility is that these anomalies are not flaws but features. They could be the faint echoes of a pre-inflationary universe, a time when the cosmos was not yet perfectly smoothed by the incredible expansion of inflation. Perhaps the universe before inflation had its own complex structure and topology, and the inflationary process did not completely erase all traces of it. These anomalies could be like finding a fossilized footprint on a freshly poured concrete sidewalk, a remnant of a reality that existed before the foundation of our current cosmos was set. In this view, the search for these statistical oddities is not about finding errors in our model, but about using them as an archaeological tool to dig deeper into the universe's history than we ever thought possible. This leads to an even more radical idea about the shape of space itself, the possibility of a non-trivial topology. Our standard assumption is that the universe is simply connected and infinite, like an endless flat plane. But what if, on the largest scales, the universe is finite and has a more complex, multiply-connected shape, like a torus or a dodecahedron? If the entire universe were smaller than the distance we can observe, then the light from distant galaxies could wrap around this finite space and multiple images of the same object could appear in different parts of the sky. While we haven't seen clear evidence of this ghostly mirroring of galaxies, the cosmic microwave background provides a much more sensitive probe. A finite universe with a non-trivial topology would impose a specific kind of symmetry on the pattern of temperature fluctuations. It would create matching circles, correlated patterns of hot and cold spots on opposite sides of the sky. The search for these correlated circles is a direct hunt for the geometric symmetry of the cosmos itself. Finding them would be one of the most profound discoveries in all of science, revealing that the entire universe is a finite, symmetrical object, a cosmic crystal with a hidden, ordered shape. The ongoing analysis of the cosmic microwave background is therefore a grand forensic investigation into the symmetry of our origins. Every subtle correlation, every unexpected statistical quirk is a potential clue. They could point toward modifications of the inflationary paradigm, evidence for multiple periods of inflation, or even hints of new physics operating at energy scales far beyond anything we can ever hope to reach with a particle collider. The symmetries we are searching for are not the simple rotations of a cube, but the fundamental statistical and geometric rules that govern the quantum birth of spacetime. The cosmic microwave background is the ultimate palimpsest, and we are only just beginning to learn how to read the faint, hidden writing that lies beneath its primary text. Now we arrive at a theory of such breathtaking mathematical beauty and ambition that it stands as a modern monument to the power of symmetry in physics. This is the E8 theory, a proposal that the entire universe, with all its forces and particles, might be nothing more than a shadow, a projection of the intricate geometry of a single, extraordinary mathematical object, the E8 Lie group. To call this idea ambitious would be a profound understatement. It is an attempt to find the cosmic Rosetta Stone, a single structure from which every law of nature can be translated. To understand why E8 is so special, we need to step into the world of Lie groups. These are not groups of people, but mathematical structures that describe continuous symmetries. Think of the simple symmetry of a circle. You can rotate it by any angle and it looks the same. The group that describes those rotations is a simple Lie group. Now imagine a symmetry that is not of a shape in space, but of the very abstract space in which the laws of physics themselves live. The standard model of particle physics is built upon a specific Lie group, SU3 times SU2 times U1. This group describes the symmetries associated with the strong nuclear force, the weak nuclear force, and electromagnetism, respectively. Gravity, described by general relativity, has its own symmetry based on the curvature of spacetime. The grand dream of unification is to find a single, larger Lie group that contains all of these smaller groups as subgroups, a master symmetry from which all others descend. Out of the classification of all possible simple Lie groups, E8 emerges as a uniquely captivating candidate. It is the largest and most complex of the 5 exceptional Lie groups. Its structure is not something easily visualized. It is a 248-dimensional mathematical object of profound complexity and beauty. To a mathematician, E8 is a masterpiece, Its root system, the fundamental vectors that define its symmetry, can be arranged in a stunning 8-dimensional pattern that is perfectly self-symmetric and incredibly rich. The number 248 isn't arbitrary. It is the number of dimensions needed to describe all the symmetry transformations this group can perform. The proposal, most famously advanced by physicist Garrett Lissy in his An Exceptionally Simple Theory of Everything, is that each of these 248 mathematical dimensions corresponds to a fundamental field in our universe. The various particles and forces we observe would then simply be different manifestations of the vibrations or excitations within this single, majestic E8 structure. The potential power of this idea is staggering. In one elegant framework, it could unify all known particles, the fermions, the matter particles like electrons and quarks, and the bosons, the force carriers like photons and gluons, would all find their places as different facets of the same geometric gem. The 3 generations of matter particles, a replication that has long puzzled physicists, could arise naturally from the structure of E8. Even gravity, the force that has stubbornly resisted inclusion in the standard model, would be woven into the fabric of this theory through its connection to the Poincaré group, which describes the symmetries of spacetime. The dream is that by studying the intrinsic geometry of E8, we could, in principle, derive every fundamental constant, every particle mass, and every force strength not from experiment, but from pure mathematical consistency. It would be a universe where physics is ultimately geometry. However, this breathtaking vision is not without its formidable challenges and controversies. The most significant hurdle is the issue of chirality. Our observed universe is chiral. The weak nuclear force interacts only with left-handed particles, a fundamental asymmetry that is absolutely crucial for the structure of reality as we know it. While the standard model incorporates this chirality naturally, it has proven incredibly difficult to extract this handedness from a grand unified theory based on E8. The group itself is chiral, but the process of breaking its vast symmetry down to the much smaller symmetry of the standard model must perfectly preserve this left-right asymmetry in just the right way, and no one has yet found a convincing and natural mechanism for this to occur within the theory. Furthermore, the theory, in its original formulation, struggles to accommodate the existence of massive particles like the Higgs boson in a way that matches our precise experimental observations. Despite these challenges, the allure of E8 endures. It represents a pole star for a certain kind of theoretical thinking, one that believes the ultimate laws of the universe must be founded on a principle of supreme mathematical elegance. The ongoing research into this area is not just about making one specific model work. It is about exploring the very limits of how deep symmetry can go in explaining existence. Even if the specific proposal that E8 is the theory of everything proves incorrect, the journey of exploring it deepens our understanding of representation theory, geometry, and the profound ways in which abstract mathematics might be woven into the physical cosmos. It is a bold gamble on the idea that the universe is not just described by mathematics, but that it is mathematics, and that at its heart lies a symmetry so beautiful and complex that we are only just beginning to glimpse its outline. Yet as we explore these grand unified symmetries of particles and cosmos, we discover that the same elegant principles might be whispering through the very fabric of life itself. For centuries, we've admired the obvious symmetries in nature, the radial symmetry of a starfish, the bilateral symmetry of a human face, the spiral symmetry of a nautilus shell. But what if these visible patterns are merely the surface manifestations of a far deeper, more fundamental symmetry operating at the molecular and evolutionary level? This leads us to a breathtaking possibility that the same mathematical principles governing the forces of the universe might also be the hidden architects of life. Consider the process of protein folding, one of biology's most fundamental and mysterious dances. A protein begins as a simple, linear chain of amino acids, a floppy string of chemical beads. Yet, in a matter of milliseconds, this string spontaneously folds itself into an exquisitely precise, three-dimensional shape. This isn't a random crumpling. It's a flawless execution of a blueprint, a transformation into a structure that allows it to perform its specific function, whether it's catalyzing a reaction, fighting a pathogen, or carrying oxygen. For decades, how this chain finds its one perfect configuration among an astronomical number of possible wrong ones. The so-called Levinthal's paradox seemed almost magical. The emerging answer appears to be rooted in a form of functional symmetry. The folding pathway, the journey the protein takes, is guided by principles of energy minimization and evolutionary optimization that are deeply symmetric. The protein doesn't try every possible fold. It follows a funnel-like energy landscape, a symmetric gradient that smoothly guides it toward its lowest energy, most stable state. This landscape isn't random chaos. It possesses a kind of structural symmetry that allows for efficient and reliable folding. Furthermore, the final protein structures themselves are often strikingly symmetric. Many are built from repeating subunits that assemble into symmetrical rings, barrels, or helices. This isn't just for show. This symmetry is functional. It creates stable structures, provides redundant active sites, and allows for allosteric regulation, where a change in one part of the molecule symmetrically affects another distant part. The symmetry we see in a protein's architecture is a direct reflection of the symmetric principles of physics and chemistry that govern its formation and function. This organizational symmetry extends upward to the very architecture of the cell. Look at the cytoskeleton, the intricate scaffolding that gives a cell its shape and enables it to move and divide. This dynamic network is built from filaments like actin and microtubules. Microtubules, in particular, are stunning examples of biological symmetry. They are hollow cylinders constructed from 13 parallel protofilaments, each made of a repeating pattern of tubulin proteins. This highly symmetric structure is not an accident. It is essential for their function. It provides tremendous strength and flexibility, but the real magic happens during cell division. When a cell prepares to divide, it assembles the mitotic spindle, a structure made of microtubules that will pull the chromosomes apart. This spindle is a masterpiece of dynamic radial symmetry. It is a bipolar structure with two centrosomes acting as symmetrical poles, and the microtubules radiating outward from them to form a perfectly symmetrical apparatus that ensures each new daughter cell receives an identical set of chromosomes. The symmetry of this process is what ensures the fidelity of life generation after generation. This precise geometric organization emerges from the self-assembly of individual molecules, guided by symmetric interaction rules that are written in the language of physical chemistry. Perhaps the most profound hidden symmetry in biology is the one operating on the grandest scale of all, evolution by natural selection. At its heart, evolution is a process that explores a vast landscape of possible forms, a concept known as a fitness landscape. Imagine a mountainous terrain where the height of a peak represents a high level of fitness, a successful, well-adapted organism. Evolution is the process of populations climbing these peaks. Now, this landscape itself may possess deep symmetries. Certain solutions to survival problems might be functionally equivalent, even if they look different. For instance, the wing of a bird, the wing of a bat, and the wing of an insect all serve the same function: flight, but evolved from completely different ancestral structures. This is called convergent evolution, and it reveals a symmetry in the problems posed by the environment. The peak of being a flying creature can be reached by multiple, symmetric evolutionary pathways. The environment presents a challenge, a symmetric set of constraints and opportunities, and life finds multiple symmetric solutions. This suggests that the space of possible biological forms is not a random scatter plot, but is structured by these symmetric attractors, these highly fit solutions that act like magnets for evolutionary innovation. The incredible repetition of certain patterns, the camera-like eye, evolving independently in cephalopods and vertebrates, the streamlined body shape evolving in dolphins, ichthyosaurs, and sharks points toward a deep, hidden symmetry in the laws of form and function. Evolution is not a purely random walk. It is a search through a possibility space that is sculpted by physical and mathematical constraints, many of which are inherently symmetric. The endless forms most beautiful, as Darwin called them, may be variations on a set of deeply symmetrical themes composed by the laws of physics and mathematics. After exploring the profound symmetries hidden within black holes, biological structures, and the cosmic microwave background, we arrive at the most ambitious quest in all of physics, the search for a final theory, a single, ultimate symmetry from which all laws of nature and every particle and force could be derived. This isn't just about unifying the known forces. It's the dream of discovering a master principle so elegant and all-encompassing that the entire universe would appear as a necessary consequence of its mathematical beauty. Throughout this journey, we've seen how symmetries act as cosmic architects, shaping everything from the quantum realm to the large-scale structure of the cosmos. The tantalizing question is whether all these individual symmetries are themselves just fractured reflections of one pristine, primordial symmetry that existed at the very beginning of everything. This monumental pursuit takes many forms, each approach a different path up the same mountain. Supersymmetry offers a compelling step by proposing a hidden partnership between matter and force particles, a symmetry that would elegantly solve several deep problems and point toward a more unified reality. String theory takes this even further, suggesting that the fundamental entities are not particles but vibrating strings, and that the properties of those vibrations, and thus all of physics, are determined by the symmetrical shape of the hidden extra dimensions they reside in. Loop quantum gravity approaches the problem from another angle, seeking to find symmetry in the very fabric of spacetime by quantizing it into discrete loops. Meanwhile, the astounding successes of the conformal bootstrap program demonstrate that the sheer requirement of self-consistency and symmetry can sometimes be enough to uniquely determine the laws of a universe. All these frameworks, in their own way, are striving toward the same goal: to find the foundational symmetry that was present at the moment of creation, before the spontaneous breaking that gave rise to the diverse and complex reality we experience today. The ultimate vision is a principle of such profound simplicity that it could be written on a T-shirt, yet so powerful that its mathematical unfoldment would generate the entirety of existence. Imagine a single equation, or perhaps even a single geometric object like the E8 group we discussed, whose intrinsic properties dictate every fundamental constant, every force strength, and every particle mass. In this view, the universe isn't just described by mathematics, it is mathematics. The apparent complexity and randomness we see would be an illusion, a necessary outcome of this core symmetry breaking into the rich patterns we observe, much like a perfectly symmetrical seed grows into a complex branching tree. The search for this final theory is therefore a search for the cosmic DNA, the fundamental code that would explain not just how the universe works, but why it is this particular universe and not another. Yet this grand quest is met with profound challenges and philosophical questions. If such a theory exists, would it be unique? Or could there be multiple, equally valid ultimate symmetries that each give rise to a different set of physical laws, leading to the controversial idea of a multiverse? Furthermore, can a theory based purely on abstract mathematics and symmetry ever truly explain the specific, contingent facts of our universe, such as why the cosmological constant has the value it does? The journey toward a final theory is as much a philosophical exploration as a scientific one, forcing us to confront the very nature of explanation and whether the human mind is even capable of grasping the ultimate logic of reality. It represents the pinnacle of our species' intellectual ambition, the relentless drive to find order in the cosmos and to understand our place within a universe that may, at its heart, be the most beautiful and symmetrical of all possible things. From the elegant dance of supersymmetric particles to the mind-bending holographic projection of our three-dimensional reality, the sheer diversity of these 30 theories paints a breathtaking portrait of a cosmos governed by profound and hidden order. We've journeyed through concepts where dimensions curl into intricate shapes, where forces unite through geometric whispers, and where the very mass of particles emerges from a cosmic field's broken symmetry. Each theory, from the established pillars of the Standard Model to the speculative frontiers of string theory and emergent spacetime, represents a different strand in a single, magnificent tapestry, a tapestry where symmetry is not just a feature of the universe, but perhaps its very foundation. This incredible journey suggests that beneath the apparent chaos of exploding stars, swirling galaxies, and quantum fluctuations, there exists a deep mathematical architecture. The laws of physics, the constants of nature, and the very stage of spacetime itself might all be expressions of an ultimate primordial symmetry, a master equation or geometric form from which all of existence unfolds. It's a powerful idea that the universe is not just described by mathematics, but that it is mathematics, a necessary consequence of elegant and self-consistent principles. The search for this hidden symmetry is more than a scientific endeavor. It is a fundamental human quest to find meaning and order in the magnificent, overwhelming complexity of the cosmos. As we conclude this exploration, the conversation doesn't have to end here. We want to hear from you. Which of these hidden symmetries resonated most deeply? Was it the cosmic hologram principle, the elegant promise of supersymmetry, or the radical idea of emergent spacetime? Share your favorite theory in the comments below and tell us why it captures your imagination. These discussions are where the next great leap in understanding might begin. If you've enjoyed this journey to the edge of our understanding, make sure to subscribe and hit the notification bell. We're constantly exploring the universe's greatest mysteries, from the nature of consciousness to the search for alien life, and we'd love for you to join us on the next adventure into the unknown. Thank you for watching.